Hello there, and welcome to Just About Earth, where curiosity slows its pace, science takes a deep breath, and big questions are allowed to unfold without any hurry at all. This is a quiet place to think gently about the planet beneath your feet, the skies above your head, and the long stories written into stone, ice, and time itself. Whether you're listening late at night, early in the morning, or somewhere in between, I am glad you are here, settling in for a while. Tonight, we're going to explore a thought that drifts somewhere between geology, climate, and imagination, but stays firmly rooted in what the Earth itself can tell us. We're going to ask what might have happened if one of the greatest shifts in the planet's shape also nudged it toward one of its coldest chapters. What if the Great Ice Age did not arrive suddenly or mysteriously, but began quietly, patiently, when the supercontinent Pangea started to come apart? It is an idea that sounds dramatic at first, as if continents cracking could instantly summon glaciers and endless snow. But the reality, as always with Earth, is slower, more subtle, and far more interesting. Nothing happens all at once. Nothing announces itself loudly. Instead, the planet changes through small adjustments layered over millions of years, each one barely noticeable on its own, yet powerful when combined. Before we go any further, let me ask you something simple. Where are you listening from right now? What does the air feel like around you? Is it warm, cool, dry, or heavy? And what time is it where you are? These little details matter because our story tonight is about how deeply place, time, and climate are connected, even when those connections stretch across entire continents and geological ages. If you find this kind of slow exploration soothing, or if learning about Earth helps your thoughts ease into a calmer rhythm, you might consider liking the video or subscribing to the channel. It helps this quiet corner of science reach others who enjoy winding down with long stories about the planet we live on. And now, without any rush at all, let us begin easing into the question itself. To understand what it would mean for an ice age to begin as Pangea broke apart, we first need to gently set aside how we usually think about continents. On maps, they look fixed and confident, as if they have always been exactly where they are now. Oceans seem permanent, coastlines feel familiar and stable. But this sense of stability is a recent illusion created by human lifespans being very short compared to Earth's. For most of its history, the planet has been rearranging itself constantly. Continents drift, collide, tear, and reshape the flow of air and water over timescales so long that even mountains struggle to keep up. Pangea was not Earth's first supercontinent, and it will not be the last, but it was one of the most complete. Nearly all of the planet's land gathered into a single enormous mass, stretching from pole to pole surrounded by a vast global ocean. When the world was arranged like this, climate behaved very differently. With so much land concentrated in one place, interior regions were far from the moderating influence of oceans. Summers could be intensely hot, winters could be harsh and dry, rainfall patterns were extreme, and large areas may have resembled endless deserts. Meanwhile, the poles were connected to the rest of the landmass, allowing heat to move north and south across continents, rather than being isolated by water. Now imagine that configuration slowly beginning to change. Not with a bang or a sudden break, but with cracks opening along ancient weaknesses in the crust. Magma pushing upward, rifts forming, shallow seas creeping in. At first, these changes would have seemed insignificant on a planetary scale. A narrow seaway here, a widening rift valley there. But Earth's climate system is sensitive, not fragile but responsive. Change the shape of the continents, and the atmosphere notices. Air moves differently when coastlines shift. Ocean currents respond when new passages open or old ones close. Heat no longer travels the same routes. Moisture patterns shift, and over long stretches of time, these adjustments can cool a planet without any single dramatic trigger. This is where the idea becomes intriguing. Instead of imagining an ice age as something imposed from outside, such as a sudden drop in solar energy, or an unlikely cosmic event, we can imagine it emerging naturally as Earth reorganizes itself. Pangea's breakup did not just create new oceans, it created new ways for the planet to lose heat. When continents cluster together, they trap warmth. When they spread apart, they allow heat to escape more efficiently into the oceans and eventually into space. Newly formed coastlines increase evaporation. Expanding oceans store and circulate cold water more effectively. Polar regions, once connected to warmer land, can become isolated and begin cooling more rapidly. But none of this happens quickly. Ice does not appear overnight. Snow must fall, survive summer, and accumulate. For that to happen, temperatures must dip just low enough, just often enough, in just the right places. Small changes stack quietly, year after year, century after century, until ice becomes a permanent feature rather than a seasonal visitor. There is also another slow player in this story, one that works almost invisibly, but leaves clear signatures in the rocks: carbon dioxide. Volcanic activity during continental breakup releases vast amounts of carbon dioxide into the atmosphere at first, which can warm the planet. But over time, freshly exposed rock reacts with rainwater, pulling carbon dioxide out of the air through chemical weathering. This process accelerates when continents fragment, because more coastline and more exposed rock mean more opportunities for carbon to be locked away. So while early stages of breakup might bring warmth, the long-term trend can reverse. Cooling creeps in, not as a dramatic plunge, but as a gradual lowering of the planet's baseline temperature. Winters linger slightly longer. Summers fail to melt all the snow in high latitudes. Ice caps begin to stabilize. What makes this idea especially compelling is that Earth has done similar things before. There have been periods in deep time when continental arrangements coincided with global cooling, and others when different arrangements favoured warmth. The planet does not choose one climate forever. It responds to its own shifting geometry. As you listen to this, it may be tempting to imagine vast frozen landscapes appearing suddenly as continents split apart. But that would miss the true character of Earth's changes. The real story is quieter. It unfolds so slowly that no single generation of organisms would notice it happening. Forests would retreat gradually. Species would migrate over thousands of generations. Ice would creep forward at a pace measured in millimeters per year. This is also why the question is framed as a what-if. We are not asking whether Pangea's breakup caused a specific ice age in a simple, direct way. We are asking whether the conditions created by that breakup could have gently tipped the balance, allowing ice to gain a foothold where before it could not survive. As we move forward, we will stay grounded in evidence. Rocks, isotopes, fossil distributions, and ancient climate indicators all give us clues. None of them speak loudly. None of them tell a complete story on their own. But together, they form a picture of a planet that responds to its own movements in complex and sometimes unexpected ways. For now, it is enough to hold the image of a single vast continent beginning to loosen its grip on itself, cracks forming, seas creeping in, winds finding new paths, currents learning new routes, and far to the north and south, snow lingering just a little longer than it used to, year after year, quietly testing whether it might stay. When the world was one vast continent, Earth behaved in ways that feel almost unfamiliar to us now. Not strange or dramatic in a cinematic sense, but quietly different, shaped by distances and connections that no longer exist. To picture it clearly, it helps to let go of modern coastlines entirely. There were no familiar oceans separating continents, no Atlantic widening each year, no Pacific framed by scattered land masses. Instead, nearly all dry land was stitched together into a single immense body, a continuous stretch of crust that wrapped around the planet like a heavy cloak. This landmass, which we call Pangea, was not simply large. It was cohesive in a way that fundamentally altered how heat, moisture, and air moved across the globe. From the equator to the poles, land connected land without interruption. If you could have walked across it, given enough time and stamina, you could have travelled from one end of the world to the other without ever seeing an open ocean. That alone changes everything. Oceans in the modern world act as enormous buffers. They absorb heat slowly and release it just as slowly. They soften temperature extremes. They carry warmth poleward and cold water toward the equator. They store energy, redistribute it, and moderate climate in ways that land simply cannot. When land dominates instead, those moderating effects weaken. In the heart of Pangea, far from any coastline, conditions were likely extreme. Summers would have been long, dry, and punishingly hot. Winters, by contrast, could swing sharply toward cold, with little moisture to soften the temperature drop. Without nearby oceans to deliver rain or retain warmth, the interior of the supercontinent behaved like an exaggerated version of today's largest continental interiors, only magnified many times over. But this was not a uniform desert world. Along the edges of Pangea, where land met the surrounding global ocean, climates were gentler. Moist air could move inland from the coast, bringing rain and seasonal variation. Forests thrived in some regions. Rivers carved long paths across the continent, fed by rainfall that followed predictable patterns shaped by the continent's immense bulk. The sheer size of Pangea influenced atmospheric circulation. Air warmed near the equator would rise, move poleward, cool, and sink, creating vast circulation cells that were stretched and distorted by the uninterrupted land surface. Monsoon-like systems likely developed, with powerful seasonal winds driven by the contrast between rapidly heating land and the slower warming ocean beyond the coast. These systems would have been stronger than anything we experience today. When such a massive landmass heats up, it pulls in air from surrounding regions with tremendous force. Seasonal rains could arrive intensely, then vanish for long stretches. Life adapted to these rhythms, evolving strategies to survive long dry periods followed by sudden abundance. At higher latitudes, the story becomes even more interesting. Because Pangea extended toward both poles, land existed where today there is mostly ocean. This meant that polar regions were not isolated islands of ice surrounded by water, but connected to warmer areas by continuous land corridors. Heat could move across the surface more easily, carried by winds and migrating organisms alike. This connection likely prevented extreme polar cooling during much of Pangea's existence. Snow could fall, but it struggled to persist year-round unless conditions were just right. Summers, even in high latitudes, would bring enough warmth to melt accumulated snow, resetting the system each year. Permanent ice sheets require not just cold winters, but summers that fail to undo the winter's work. Another important factor was sea level. During much of Pangea's tenure, sea levels fluctuated, sometimes flooding shallow continental margins and creating vast inland seas. These seas acted as temporary climate moderators, bringing moisture deeper into the continent and softening temperature extremes locally. But they were unstable features, appearing and disappearing as tectonics and climate shifted. Beneath all of this, the crust itself was under strain. Pangea did not assemble easily, and it did not remain stable without consequence. The forces that brought continents together also thickened crust in some areas, raised mountain ranges, and stored energy that would later contribute to the supercontinent's breakup. Mountain belts formed along collision zones, influencing weather patterns by redirecting winds and altering rainfall. Mountains matter more than they might seem. They force air upward, cooling it, and causing moisture to fall as rain or snow. In a supercontinental setting, large mountain ranges could create rain shadows hundreds or even thousands of kilometers long, shaping ecosystems far beyond their immediate slopes. These features added complexity to an already extreme climate system. Life during this time adapted to a world of long distances and dramatic gradients. Species ranges could stretch across enormous territories without crossing oceans. Migration routes were uninterrupted. Evolution unfolded under conditions where isolation was harder to achieve, slowing diversification in some cases while encouraging resilience and adaptability in others. Plants developed strategies to survive drought and temperature swings. Animals evolved behaviors to cope with seasonal extremes. Entire ecosystems pulsed with the rhythms imposed by the planet's unified geography. It was a world that rewarded endurance and flexibility more than specialization. From a climate perspective, Pangea represented a kind of balance point, not a stable equilibrium in the modern sense, but a configuration that maintained certain patterns for long periods. Heat built up in the interior and was released at the margins. Moisture cycled unevenly but predictably. Ice struggled to gain a permanent foothold because the conditions required for long-term accumulation were not consistently met. Yet beneath this apparent balance, small vulnerabilities existed. Climate systems do not need dramatic disruptions to shift. Sometimes they only need the removal of a stabilizing factor. In Pangea's case, that stabilizing factor was connectivity. The continuous landmass allowed heat and energy to spread in ways that prevented runaway cooling. Once that connectivity began to weaken, even slightly, the system became more sensitive. Narrow seaways opening between land masses could interrupt heat transfer routes. Coastal lengths increased. Ocean influence expanded. These changes did not immediately overturn the climate, but they introduced new variables into an already complex system. It is also worth remembering that Earth's climate operates on feedbacks. Cooling encourages ice formation. Ice reflects sunlight. Reflection leads to further cooling. But for this loop to start, ice must first survive the melt season. Pangea's configuration made that difficult over most of its surface, especially when land connections allowed warmth to flow toward colder regions. The presence of land at high latitudes did not guarantee ice sheets. Without the right circulation patterns and isolation, those regions remained marginal, cold but not frozen solid year-round. Snow might blanket the ground in winter, only to vanish again with the return of the longer days and higher sun angles. As long as Pangea remained intact, the planet leaned toward a climate that resisted deep freezing. Not because it was warm everywhere, but because it lacked the structural conditions that favour persistent ice growth. The world could cool somewhat or warm somewhat, but it struggled to tip fully into a prolonged glacial state. This is why the idea of an ice age beginning as Pangea broke apart is not only plausible, but compelling. The supercontinent itself acted as a brake on certain climate shifts. Its breakup removed that brake gradually, allowing new patterns to emerge. But before any ice could advance, before oceans could fully reshape circulation, before carbon cycles could respond to newly exposed rock and seafloor, the world had to exist in this unified state. A single landmass breathing in seasonal rhythms, storing heat unevenly, and quietly accumulating the stresses that would eventually pull it apart. Understanding that world is essential because it reminds us that Earth's climate is not driven by a single lever. It is shaped by geometry, movement, and time. Pangea was not just a backdrop for life. It was an active participant in shaping the planet's long-term climate behaviour. As cracks began to form deep within its crust, long before any ocean was wide enough to name, the climate system was already poised to respond. The conditions that once favoured balance would slowly give way to conditions that allowed cold to linger, snow to persist, and ice to begin its patient advance. And with that slow loosening of a once unified world, the stage was set for something entirely different to begin taking shape. Not all at once, not dramatically, but steadily, as Earth always prefers to do. The long, quiet cracking of Pangea did not announce itself with earthquakes felt across the globe or oceans suddenly pouring into massive chasms. There were no witnesses to gasp at the moment the supercontinent began to fail. Instead, the process unfolded so slowly that even the rocks themselves seemed unaware of what was happening at first. What we call the breakup of Pangea was not a single event, but a drawn-out sequence of small changes accumulating over tens of millions of years, each one subtle on its own, yet transformative when taken together. Deep beneath the surface, forces that had once pulled continents together began to reverse their direction. Heat built up in the mantle, the thick, slowly moving layer of rock beneath Earth's crust. That heat did not rise evenly. It gathered in pockets, forming broad upwellings that pressed upward against the base of the continent. The crust above responded the only way it could. It stretched. Stretching continental crust does not look dramatic at first. Rock does not tear cleanly. It thins. It fractures gradually. Long valleys form as the surface sags under tension. These rift valleys were the earlier signs that Pangea was no longer stable. They appeared quietly, often far inland, nowhere near any existing coastline. To anyone living at the surface at the time, they would have looked like wide, shallow depressions, perhaps dotted with lakes and volcanic features, not the beginnings of future oceans. As the crust thinned, magma from below found easier pathways upward. Volcanic activity increased along these rifts, releasing heat and gases into the atmosphere. Lava flows spread across the land, cooling into new rock that recorded the direction of Earth's magnetic field like a timestamp. Today, those magnetic signatures help scientists trace the earliest phases of continental separation, even when erosion has erased much of the surface evidence. This volcanic phase mattered for climate in complicated ways. On short timescales, volcanic eruptions release carbon dioxide, a greenhouse gas that can trap heat and warm the planet. But on longer timescales, the same volcanism creates fresh rock surfaces that react chemically with rainwater, pulling carbon dioxide back out of the atmosphere and locking it into minerals. Warming and cooling were not opposites here. They were part of the same slow cycle. While rifting progressed, the land above began to lower. Thin crust sits lower than thick crust, just as a thinner piece of wood floats lower in water. As valleys deepened, they became natural basins. Rainwater collected. Rivers changed course. In some regions, long, narrow lakes formed, precursors to the shallow seas that would follow. These bodies of water introduced something new into the heart of the continent: moisture. Even before any true ocean existed, the presence of inland water began to alter local climate patterns. Evaporation increased humidity. Rainfall patterns shifted. Seasonal contrasts softened slightly in some regions, while becoming sharper in others. None of this was dramatic on a global scale, but climate systems respond to gradients, not absolutes. Small differences matter. The cracking of Pangea did not happen everywhere at once. Some regions remained stable while others stretched and thinned. This unevenness created a patchwork of environments across the supercontinent. In some areas, tectonic calm persisted for millions of years. In others, rifting accelerated, carving long scars that would eventually widen into ocean basins. One of the most important consequences of this uneven breakup was the gradual increase in coastline length. Even before continents fully separated, shallow seas flooded low-lying regions, creating extensive coastlines deep within what had once been continental interior. Coastlines are powerful climate influencers. They are where land and ocean exchange heat, moisture and energy most efficiently. As coastlines crept inward, the continent's ability to retain heat weakened. Water absorbed warmth during warmer seasons and released it slowly, moderating temperature extremes nearby. This may sound like a stabilizing influence, and locally it was, but globally it represented a shift away from the tightly coupled land-dominated system that had characterized Pangea. At the same time, the developing rifts disrupted long-established wind patterns. Air circulation that had once flowed uninterrupted across thousands of kilometers of land now encountered barriers, pressure differences and new moisture sources. Seasonal wind systems adjusted. Some regions grew wetter, others dried out further. Climate zones began to fragment, just as the land itself was fragmenting. Beneath these surface changes, something equally important was happening in the oceans that did not yet exist in their modern form. As rifts widened and subsided, seawater eventually spilled in from the surrounding global ocean. These early seas were shallow, warm and narrow, but their impact was outsized. They introduced saltwater circulation into areas that had never experienced it before. Once seawater entered a rift, the process became difficult to stop. Water added weight, causing further subsidence. Subsidence allowed more water in. Over time, this feedback deepened the basins, widened the seaways, and accelerated separation. What began as a crack became a corridor. What became a corridor slowly evolved into an ocean. This matters because ocean circulation is one of the most powerful regulators of Earth's climate. Even narrow seaways can redirect currents, altering how heat moves from the equator toward the poles. During Pangea's early breakup, these changes were small but cumulative. Each new connection allowed water to take a slightly different path, shifting heat distribution bit by bit. Another subtle but crucial effect involved Earth's reflectivity. Land and ocean absorb sunlight differently. Dark ocean water absorbs more solar energy than many land surfaces, but it also stores that energy and redistributes it. As ocean area increased relative to land, the planet's overall energy balance began to shift. Where and how heat was stored became just as important as how much heat arrived from the sun. At higher latitudes, these changes had special significance. As continental connections weakened, heat transport toward the poles became less efficient in certain directions. Regions that had once received warmth via land-based atmospheric circulation became more isolated. This did not immediately freeze them, but it nudged average temperatures downward over long spans of time. The cracking of Pangea also influenced sea level globally. As new ocean basins formed, they initially displaced water, raising sea levels and flooding continental margins. Later, as the basins deepened and cooled, sea levels could fall. These fluctuations reshaped coastlines repeatedly, creating cycles of flooding and retreat that affected sedimentation, ecosystems, and climate feedbacks. Sediments deposited during this time preserve a quiet record of change. Layers of sandstone, shale, and limestone tell stories of shifting shorelines, alternating wet and dry conditions, and gradual cooling trends in some regions. Fossils within those layers show species adapting, migrating, or disappearing as environments transformed around them. It is important to emphasize how gradual all of this was. The term breakup can be misleading. It suggests a sudden event, a snapping apart. In reality, Pangea loosened its grip slowly, like fabric fraying along multiple seams. For millions of years, the supercontinent was neither fully intact nor fully separated. It existed in an in-between state, with partial connections and emerging divisions. This in-between state is especially important for understanding how an ice age could begin without anyone noticing at first. Climate tipping points rarely involve instant change. They involve thresholds crossed quietly. A few more winters where snow lasts longer. A few summers that fail to fully melt high-latitude ice. A few adjustments in ocean circulation that favour cooling over warmth. During the early cracking of Pangea, all of these conditions began lining up, not dramatically but persistently. The planet was not racing toward ice. It was simply becoming more permissive of it. The safeguards that once prevented long-term ice accumulation were weakening one by one. Volcanic activity too played a dual role. While eruptions added greenhouse gases, they also produced aerosols that reflected sunlight in the short term. Over geological timescales, volcanic provinces associated with rifting increased weathering rates, drawing down atmospheric carbon dioxide and encouraging cooling. These processes overlapped rather than cancelled each other, creating a complex climatic signal rather than a simple trend. As continents thinned and separated, mountain ranges eroded. Erosion exposed fresh rock, further accelerating chemical weathering. Rivers carried minerals to the seas, altering ocean chemistry. These changes affected plankton, carbon burial, and the long-term carbon cycle. all of which feed back into global temperature regulation. The cracking of Pangea was not just a tectonic event, it was a planetary reorganization. Air, water, rock and life all responded in their own ways, each response feeding into the others. Climate did not drive the breakup, but it was reshaped by it continuously. From the perspective of any single moment, nothing would have seemed unusual. From the perspective of deep time, everything was shifting. The world was becoming more fragmented, more dynamic, and more sensitive to feedbacks that favour cooling. As rifts widened and early oceans took shape, Earth crossed an invisible line. It moved from a state where large-scale ice was difficult to sustain to one where ice could begin to persist if conditions aligned. That alignment did not happen immediately. It required further changes in circulation, chemistry and geography, but the groundwork was being laid. The quiet cracking of Pangea was not the start of an ice age in itself. It was the slow removal of barriers that had once kept deep cold at bay. With each new seaway and each shifting current, the planet edged closer to a configuration where ice no longer had to fight so hard to survive. Oceans slipping into the widening gaps of Pangea did not arrive like invading forces. There was no single moment when seawater suddenly claimed the land and declared a new age. Instead, the ocean moved patiently, almost cautiously, following gravity, exploiting weakness, filling low places that had been forming for millions of years. What changed was not simply where water existed, but how the entire planet exchanged heat, moisture, and energy. In a very real sense, Earth began to breathe differently. At first, the water that entered the rifts was shallow and restricted. Narrow seaways crept inland, flooding long valleys that had once been dry or dotted with lakes. These early seas were warm, influenced by their proximity to the equator and the surrounding land. They did not yet behave like modern oceans, but they introduced something fundamentally new into the climate system. They allowed continuous interaction between land and salt water over vast distances where none had existed before. Water is not passive in climate. It absorbs heat efficiently, far more efficiently than rock or soil. During warm periods, it stores that energy. During cooler periods, it releases it slowly. When oceans began to replace land in the cracks of Pangea, they created thermal reservoirs where there had once been surfaces that heated and cooled rapidly. This alone began to dampen some extremes while amplifying others. As shallow seas expanded, evaporation increased. Moisture that had once been locked into seasonal rains near the coast now entered the atmosphere more consistently. Clouds formed more readily. Rainfall patterns shifted, sometimes subtly, sometimes decisively. Regions that had been dry for millions of years experienced increased humidity. Other regions, paradoxically, dried out as circulation patterns reorganized. The atmosphere responded quickly, even though the geological changes were slow. Air moves fast compared to rock. When new bodies of water appeared, pressure gradients changed. Wind systems adjusted to the altered distribution of heat and moisture. Patterns that had been stable under a unified landmass began to fragment. One of the most important changes involved the way heat moved across the planet. When Pangea was intact, heat could travel across land relatively directly through atmospheric circulation. Warm air masses formed over the continent and moved poleward with fewer interruptions. Once oceans intruded, those pathways were broken. Air crossing water behaved differently than air crossing land. It cooled, picked up moisture, and redistributed energy in new ways. This mattered especially for high latitudes. The poles are naturally cold because sunlight arrives at a shallow angle, spreading energy thinly. To prevent permanent ice buildup, they rely on heat transported from lower latitudes. When continental connections weaken, that transport becomes less efficient. Even small reductions in poleward heat flow can tip the balance. As new ocean basins formed, they also allowed currents to develop where none had existed. At first, these currents were weak and constrained, but over time they grew stronger and more complex. warm water began flowing along new routes. Cold water found new paths toward the equator. These currents reshaped regional climates long before any global ice sheets appeared. Ocean circulation acts like a planetary conveyor belt. It redistributes heat far more effectively than the atmosphere alone, but it does not distribute it evenly. Some regions warm, others cool. When continents block or redirect currents, those effects intensify. During Pangea's breakup, the opening and closing of seaways repeatedly altered these pathways. In some cases, warm equatorial water could no longer reach higher latitudes as efficiently. In others, cold polar water gained access to lower latitudes. Each adjustment nudged average temperatures slightly. No single change caused an ice age, but each one moved the system closer to conditions where ice could persist. Another crucial factor was salinity. As seas flooded continental interiors, evaporation left behind salt, increasing the density of surface waters. Dense water sinks more readily, driving deep ocean circulation. This sinking motion pulls surface water toward it, strengthening currents. Over time, these processes helped establish vertical circulation patterns that allowed cold, deep water to spread more widely. Deep ocean circulation is particularly effective at locking cold into the system. Once cold water sinks, it can remain isolated from the atmosphere for centuries or longer. This acts as a long-term cooling mechanism, slowly lowering average ocean temperatures and reinforcing cooler climates. At the same time, newly formed coastlines increased weathering rates. Rain falling on land reacts chemically with exposed rock, especially fresh volcanic rock produced during rifting. This process removes carbon dioxide from the atmosphere. The more coastline and exposed rock there is, the faster this removal can proceed. Carbon dioxide does not vanish instantly, but over millions of years, enhanced weathering can significantly reduce atmospheric concentrations. Lower carbon dioxide means less heat trapped near the surface. Cooling follows, gradually but persistently. What makes this especially interesting is the timing. Volcanism associated with rifting initially released large amounts of carbon dioxide, potentially warming the planet. But as rifting slowed and continents separated further, weathering outpaced volcanic input. The long-term signal shifted from warming to cooling. Oceans slipping in accelerated that transition. Moisture also played a role in a less obvious way. Increased evaporation led to more snowfall at higher latitudes, provided temperatures were low enough. Snowfall alone does not create ice sheets. Snow must survive the melt season. But once cooling nudges summer temperatures just low enough, increased snowfall can tip the balance. Snow reflects sunlight efficiently. This reflectivity, known as albedo, reduces the amount of solar energy absorbed at the surface. Less absorbed energy means cooler temperatures, which allow more snow to persist. This feedback loop is powerful, but it only activates when conditions are already close to the threshold. Ocean-driven cooling helped bring those thresholds within reach. The intrusion of oceans also changed storm tracks. Storms derive energy from temperature contrasts, especially between warm ocean surfaces and cooler air. As new seas formed, storm activity increased in some regions, redistributing heat and moisture more dynamically. These storms could deliver snow to higher elevations and latitudes, reinforcing ice-friendly conditions. Meanwhile, the expansion of ocean area relative to land altered the planet's overall heat capacity. Oceans store vast amounts of heat compared to land. As their area increased, the planet became slower to warm and slower to cool on short timescales, but more capable of sustaining long-term trends. This favoured persistent climate states over rapid oscillations. This shift toward persistence is important. Ice ages are not brief events. They require stability. Once ice begins to accumulate, it must be supported by a climate system that does not easily flip back to warmth. Expanding oceans contributed to that stability by buffering short-term fluctuations while allowing long-term cooling to take hold. Life responded as well. Marine ecosystems expanded into newly formed seas. Plankton populations grew, drawing carbon out of the atmosphere through photosynthesis and depositing it on the seafloor when they died. This biological pump further reduced atmospheric carbon dioxide, reinforcing cooling trends. On land, ecosystems adjusted to changing rainfall and temperature patterns. Forests retreated in some regions and expanded in others. Grasslands emerged where conditions favoured them. These changes affected soil development, erosion rates, and carbon storage, feeding back into the climate system. It is tempting to imagine the ocean as a singular force, but what mattered most was interaction. Oceans interacting with air, oceans interacting with land, oceans interacting with life. Each interaction altered the flow of energy slightly. Over millions of years, those slight alterations compounded. The phrase, "the planet starts to breathe differently," is not metaphorical in a vague sense. It reflects a literal change in how gases, heat, and moisture cycled through Earth's systems. Inhalation and exhalation took new forms. The rhythms changed. The pace remained slow, but the direction shifted. Importantly, this shift did not lock Earth into an ice age immediately. Warm periods still occurred. Tropical regions remained warm. Seasonal cycles continued, but the baseline was lowering. The average state toward which the system relaxed after disturbances was becoming cooler. This matters because climate responds to averages more than extremes. A single cold winter does not create an ice sheet. A slight lowering of average summer temperatures over millions of years can. Oceans slipping into the cracks of Pangea helped lower those averages by redistributing heat in ways that favoured cooling at the poles. As seaways widened further, connections between ocean basins increased. Eventually, global circulation patterns began to resemble something closer to the modern system, though still very different in detail. With each widening passage, the potential for large-scale heat transport changed. By this point, the planet had moved far from the tightly coupled land-dominated system of early Pangea. The world was becoming one of separated continents and interconnected oceans. This new configuration allowed cold to linger in places where it previously could not. Ice, however, still required a final push. Oceans had set the stage by reshaping circulation, chemistry, and energy storage. They had changed how the planet breathed, but other factors were still at work, quietly aligning. How moving continents rewrite wind, water, and weather is not something that happens abruptly, and it is not something the planet announces with a single dramatic shift. It unfolds through slow adjustments that compound over time, reshaping invisible systems that most life never directly perceives, yet depends on completely. Air currents, ocean circulation, and long-term weather patterns are deeply sensitive to geography. When continents move, even slightly, those systems are forced to adapt, sometimes in ways that favour warmth, sometimes in ways that quietly encourage cold. At the most basic level, wind exists because the planet is unevenly heated. The equator receives more direct sunlight than the poles, creating temperature differences that drive air movement. Warm air rises, cool air sinks, and the rotation of the Earth bends those flows into recognisable patterns. But those patterns are not fixed. They depend on where land blocks air, where oceans store heat, and where mountain ranges redirect movement. When Pangea was intact, wind systems were stretched across enormous, uninterrupted distances. Air could travel thousands of kilometres over land without encountering a coastline. This allowed massive continental-scale circulation patterns to develop, with predictable seasonal reversals driven by the heating and cooling of the supercontinent's interior. Once that landmass began to fragment, those patterns lost their continuity. As continents drifted apart, coastlines multiplied. Each coastline created a boundary where air behaved differently. Over land, air heats and cools quickly. Over water, it changes temperature slowly and picks up moisture. When wind crosses from ocean to land, or land to ocean, its temperature, humidity and stability change. Multiply those transitions across a planet, and circulation becomes more complex and less uniform. One of the first major consequences of continental movement was the weakening of large continent-spanning wind systems. Instead of one dominant pattern stretching across the interior of Pangea, multiple regional systems emerged. Some were stronger, some weaker, but all were more localized. This localization matters because it creates sharper climate contrasts and makes certain regions more vulnerable to long-term cooling. Water vapor plays a central role here. Moist air carries heat efficiently. When continents are clustered, moisture transport can be relatively direct. As land breaks apart, moisture paths become fragmented. Some regions receive more rainfall, others receive less. Importantly, high-latitude regions can lose access to moisture-laden air that once delivered warmth as well as precipitation. The movement of continents also reshapes the paths of ocean currents, which in turn influence atmospheric circulation. Warm currents heat the air above them, cold currents cool it. When currents shift, prevailing winds shift as well. These changes can reinforce one another, locking in new climate patterns. Consider what happens when a continent drifts into higher latitudes. Land absorbs less heat than ocean at those latitudes, especially during winter. Air above it cools rapidly, becoming denser and sinking. This creates persistent high-pressure systems that repel storms and trap cold air. Over time, such regions become increasingly prone to snow accumulation. Now imagine multiple continents drifting into polar or near-polar positions. The cumulative effect is a redistribution of cold land surfaces around the globe. Each one alters local circulation, but together they can influence global wind patterns, making it easier for cold air to remain in place rather than being displaced by warmer flows. Mountain building adds another layer. As continents collide or stretch, mountain ranges rise. Mountains force air upward. Rising air cools. Cooling air loses moisture as precipitation. On the windward side, this leads to rain or snow. On the leeward side, dry conditions prevail. These rain shadows can extend far beyond the mountains themselves. Snowfall on mountains is particularly important for long-term climate. Snow persists at high elevations even when surrounding lowlands warm. Persistent snow increases albedo, reflecting sunlight and cooling the surrounding air. This cooling can spread downslope and outward, subtly influencing regional climate. As continents move, mountain ranges can form in new latitudes. A range forming closer to the poles has a much greater chance of hosting permanent snow and ice. Once established, these icy regions can seed larger glaciations by cooling adjacent areas and altering wind flow. Ocean gateways are another critical factor. Narrow seaways can act as valves, controlling how water flows between ocean basins. When a continent blocks or opens a passage, it can redirect entire current systems. These redirections influence where heat is delivered and where it is removed. For example, when warm equatorial water can no longer flow freely toward the poles due to continental barriers, polar regions cool. Conversely, if cold polar water gains access to lower latitudes, it can cool vast regions of the ocean and atmosphere. Both effects favour ice formation. Weather patterns follow these currents. Storm tracks tend to form along strong temperature gradients, often near ocean fronts. When currents shift, storm tracks shift. Regions that once experienced frequent storms may become calmer and colder, others may grow wetter or more volatile. Seasonality is also affected. Continental interiors tend to experience greater seasonal swings than coastal regions. As continents break apart and interiors shrink, some areas become more maritime, reducing seasonal extremes. However, this moderation does not apply equally everywhere. High-latitude land can remain strongly seasonal, with long, cold winters that favour snow accumulation. The interaction between land position and Earth's tilt further complicates matters. Changes in continental layout alter how sunlight is distributed seasonally. A continent positioned such that it receives less summer sunlight in high latitudes is more likely to retain snow year-round. Over long timescales, this can be decisive. All of these processes interact. Wind influences ocean currents. Currents influence temperature. Temperature influences ice. Ice influences albedo. Albedo influences temperature again. Continental movement nudges each part of this system, not forcefully but persistently. It is important to note that moving continents do not guarantee cooling. In some configurations, they promote warmth. But during the breakup of Pangea, several trends aligned in a way that favoured cooling. Increased coastline length, altered heat transport, emerging ocean gateways, and shifting wind systems all worked together to lower the planet's effective temperature in certain regions. The changes were uneven. Some areas warmed even as others cooled. Tropical regions remained relatively stable. The focus is on high latitudes and elevated terrains, where small changes have outsized effects. That is where ice begins, not because those places are dramatic, but because they are sensitive. As continents continued drifting, feedback strengthened. Once ice appeared seasonally, it began influencing wind patterns by cooling the air above it. Cold air is heavier. It sinks. Sinking air suppresses cloud formation, allowing more heat to escape into space during winter nights. This reinforces cooling locally. Over time, these local effects can spread. A colder region can influence neighbouring areas through atmospheric circulation. Cold begets cold, not explosively, but gradually. This is how regional cooling becomes hemispheric cooling, and eventually global cooling. Weather variability also increased. Fragmented continents create more boundaries, more gradients, more opportunities for complex interactions. While this can lead to extremes, it also allows cold conditions to persist through variability rather than being erased by uniform circulation. Life responded to these shifting patterns by migrating, adapting, or disappearing. Vegetation changes altered surface reflectivity and carbon storage. Grasslands reflect more sunlight than forests. Tundra reflects more than grassland. Each transition fed back into the climate system. At no point did a single change dictate the outcome. The rewriting of wind, water, and weather was a collective process, driven by geography and motion. The Earth was not aiming for an ice age, it was simply responding to new constraints. As continental drift continued, the climate system explored new configurations. Some were transient, others proved stable enough to persist. The ones that favoured long-term ice accumulation did so quietly, without spectacle, simply by making it easier for cold to remain. This rewriting was still ongoing long after the first oceans slipped into the cracks. Each additional shift refined the system further. Currents strengthened, winds adjusted, seasons sharpened in some places and softened in others. The planet was no longer breathing as it once had. Its rhythms had changed. Air and water followed new paths. Weather obeyed new rules. And within those new rules, the possibility of sustained cold grew steadily stronger. The first cold whispers at the poles did not arrive as walls of ice or endless white horizons. They arrived as hesitation, as seasons that lingered a little longer than before, as snow that did not fully vanish when sunlight returned. Nothing about this stage of Earth's cooling would have looked dramatic to an observer living through it. In fact, it might have seemed unremarkable, easily dismissed as ordinary variation. But in deep time, these small hesitations mattered more than any sudden freeze ever could. Polar regions are always the most sensitive parts of the climate system. They sit at the edges of the planet's energy budget, receiving sunlight at shallow angles and enduring long periods of darkness each year. Because of this, they exist close to a threshold. A slight reduction in heat delivery can push them toward persistent cold. A slight increase can pull them back towards seasonal balance. When Pangea was intact, that balance tended to favour melting. Once the continents began to separate, the balance quietly shifted. One of the earliest changes involved summer temperatures. Ice does not depend on winter cold alone. Winters can be brutally cold without producing glaciers. What matters is whether summer warmth is sufficient to erase what winter builds. In polar regions during the early stages of continental breakup, summers began losing that erasing power. Not everywhere at once, and not by large margins, but just enough in certain regions for snow to linger. Lingering snow alters the surface immediately. Bare ground absorbs sunlight. Snow reflects it. This difference is not subtle. Snow can reflect most incoming solar radiation back into space, preventing the surface from warming. When snow survives into late summer, it reduces local temperatures further, making it more likely that snow will survive the next year as well. This feedback does not require massive ice sheets. It begins with patches. Those patches likely formed first in elevated areas. Even modest uplands near the poles can remain cooler than surrounding lowlands. As continents shifted, mountain ranges and plateaus moved into higher latitudes or rose due to tectonic forces. These high places acted as testing grounds for persistent snow. If snow could survive there, it could spread outward. At the same time, changes in ocean circulation reduced the amount of heat reaching polar coasts. Warm currents that once brushed polar regions weakened or shifted away. Cold currents gained influence. Sea ice may have begun forming seasonally along coastlines, reflecting sunlight and cooling nearby air. Sea ice does not need to be thick to matter. Its presence alone changes heat exchange between ocean and atmosphere. When sea ice forms, it insulates the ocean beneath, preventing stored heat from warming the air. This allows air temperatures to drop further, encouraging more ice formation. This feedback is particularly effective during long polar nights, when sunlight is absent and heat loss dominates. The atmosphere responded quickly to these surface changes. Cold air is denser than warm air. As polar regions cooled, air pressure increased. High-pressure systems became more persistent. These systems tend to block incoming storms, limiting the delivery of warm, moist air from lower latitudes. Reduced storm activity further cooled the region, reinforcing isolation. Isolation is crucial. Polar regions cool not just because they receive less sunlight, but because they lose contact with warmth elsewhere. When circulation patterns shift to favour isolation, cold deepens. During Pangea's breakup, several circulation changes aligned to do exactly that. Another factor was the length of polar nights. Earth's axial tilt ensures that polar regions experience months without sunlight each year. If summers become cooler, the heat gained during the brief sunlit season may no longer compensate for winter losses. Over many cycles, this imbalance accumulates. The surface cools progressively. Ice gains stability. Chemical evidence preserved in marine sediments supports this gradual cooling. Oxygen isotope ratios in microscopic shells record changes in ocean temperature and ice volume. During periods corresponding to continental breakup, these records show subtle shifts toward heavier isotopes, indicating cooling and increasing ice storage even before large ice sheets formed. Importantly, this early cooling was not uniform between the two poles. Differences in continental configuration meant that one pole could cool faster than the other. If one polar region was more isolated by land and ocean arrangements, it would experience stronger cooling first. This asymmetry is common in Earth climate history. The presence of land near a pole amplifies cooling potential. Land cools faster than ocean. Snow accumulates more readily on land. When continents drifted into higher latitudes, they provided surfaces where ice could gain a foothold. Once ice formed on land, it could persist far longer than sea ice alone. Vegetation also played a role. As temperatures dropped, plant communities shifted. Forests retreated. Tundra expanded. Tundra reflects more sunlight than forested land. It also traps snow more effectively, preventing wind from removing it. These changes further enhance surface reflectivity and cooling. Dust may have contributed as well. Changing climates altered erosion patterns, increasing dust transport to polar regions. Dust settling on snow can either darken it, promoting melting, or influence cloud formation, affecting temperature. The net effect depends on context. But dust is another reminder that many small processes interact. What is striking about this phase is how quiet it would have seemed. No dramatic ice walls, no sudden global freeze, just colder summers, longer-lasting snow and subtle changes in ecosystems. These are easy to overlook in short-term perspectives, but over millions of years they reshape a planet. The first cold whispers were not an announcement of an ice age. They were an invitation for ice to stay a little longer each year, an invitation for feedbacks to begin reinforcing one another rather than cancelling out. As cooling progressed, the polar oceans became increasingly stratified. Cold, fresh surface water sat atop denser, saltier water below. This stratification limited vertical mixing, preventing heat stored at depth from reaching the surface. Without that heat, surface waters cooled further, supporting more sea ice. Deep ocean circulation also adjusted. As cold water sank in polar regions, it spread through the deep ocean, lowering temperatures far from the poles. This created a background cooling that affected the entire planet slowly and persistently. It is important to emphasize that these processes overlapped in time. There was no clear boundary between a world without polar ice and a world with it. Instead, Earth existed in a transitional state for a very long time, with ice appearing seasonally, then persistently in some places, then spreading gradually. This transitional state is often underappreciated because it leaves subtle geological evidence. Large ice sheets carve dramatic features. Early ice leaves lighter traces. But those traces exist, and when assembled carefully they tell a story of incremental change rather than sudden catastrophe. During this time, life adapted again. Cold-tolerant species expanded their ranges. Others retreated equatorward. Migration routes shifted. Marine organisms adjusted to cooler waters. These biological responses fed back into climate through carbon cycling and ecosystem structure. The planet did not lock into a permanent ice age immediately. Warm intervals still occurred. Climatic oscillations continued. But the baseline state had changed. Cooling became easier to maintain. Warming required stronger forcing. This change in baseline is one of the most important aspects of Earth's climate evolution. It determines how the system responds to perturbations. Once the baseline lowers, events that previously would have produced minor cooling can produce major ice growth instead. The first cold whispers at the poles mark the moment when Earth crossed into a new sensitivity regime. Ice no longer needed extraordinary conditions to persist. It needed only the absence of strong warmth. As continents continued to drift, as oceans continued to widen, and as atmospheric composition continued to adjust, those whispers grew slightly louder. Not enough to dominate the planet yet, but enough to be noticed in the long record preserved in stone and sediment. From here, the story becomes increasingly intertwined with feedbacks that magnify cooling. Reflection, circulation, chemistry, and biology all begin reinforcing one another. Ice, once fragile, starts to gain resilience. Ice, albedo, and the power of reflection form one of the most quietly influential relationships in Earth's climate system. Nothing about it feels dramatic at first glance. Ice just sits there. Sunlight arrives. Some of that light goes back into space. Yet this simple exchange, repeated day after day, year after year, has the ability to reshape an entire planet's temperature. Once ice begins to linger, reflection becomes more than a side effect. It becomes an active force. To understand why this matters so much, it helps to start with what albedo actually is. Albedo is a measure of how much incoming solar radiation a surface reflects. Dark surfaces like oceans or forests have low albedo. They absorb most of the sunlight that hits them, converting it into heat. Bright surfaces like snow and ice have high albedo. They reflect a large fraction of sunlight back into space before it can warm the surface. This difference is enormous in practical terms. An ice-covered surface can reflect more than half of the sunlight that reaches it. Open ocean, by contrast, absorbs most of that energy. The same amount of sunlight can either warm the planet or be effectively discarded depending on what it strikes. When ice is seasonal and short-lived, albedo effects are limited. Snow falls in winter, reflects sunlight briefly, then melts as temperatures rise. The system resets. But when ice begins to persist across seasons, reflection stops being a temporary feature and starts becoming a permanent influence on climate. This is why the first lingering patches of snow near the poles mattered so much. They were not just cold surfaces, they were mirrors. Each surviving patch slightly reduced the amount of solar energy absorbed locally. That reduction cooled the surrounding air and ground, making it easier for nearby snow to survive as well. This process does not require large ice sheets to begin. It works just as effectively at small scales. A patch of snow on a plateau can cool the air flowing over it. That cooled air can drift downslope, lowering temperatures in adjacent regions. Those regions may then retain snow more easily the following winter. Over time, these small interactions can link together. One of the most important aspects of albedo feedback is that it is non-linear. That means its influence does not increase smoothly with ice coverage. Instead, there are thresholds. Below a certain amount of ice, the effect is modest. Once ice crosses a critical area, the cooling effect accelerates. This helps explain why Earth can remain relatively ice-free for long periods, and then enter extended glacial states without a single dramatic trigger. The system does not respond proportionally. It responds when thresholds are crossed. At high latitudes, those thresholds are easier to reach. Sunlight is already limited. The sun sits low on the horizon even during summer. Any additional reflection has an outsized impact because there is less energy available to begin with. Reflecting a small fraction of weak sunlight can make the difference between melting and survival. Another factor that amplifies this effect is the angle of sunlight. At low angles, sunlight spreads over a larger area and is more easily reflected. Ice at the poles is particularly efficient at sending energy back into space because of this geometry. As ice expands poleward or equatorward from the poles, it continues to operate in a region where reflection is highly effective. Sea ice plays a distinct role here. Unlike land ice, sea ice forms directly over water that would otherwise absorb heat. When sea ice covers the ocean, it replaces a dark, heat-absorbing surface with a bright, reflective one. This change dramatically reduces the amount of energy entering the ocean. The consequences of this are far-reaching. Oceans store heat and transport it. When less heat enters the ocean, less heat is available to be moved poleward by currents. This weakens one of the planet's primary warming mechanisms for high latitudes. Additionally, sea ice insulates the ocean from the atmosphere. While this might sound like it would trap heat below, it actually prevents the ocean from releasing stored warmth into the air during winter. Without that release, air temperatures drop further, allowing ice to thicken and expand. Thicker ice reflects even more sunlight and insulates more effectively. The feedback strengthens. This is why sea ice extent is such a sensitive indicator of climate state. Small changes in temperature can produce large changes in ice coverage, which then feed back into temperature. On land, ice sheets introduce similar feedbacks but with additional complexity. Ice sheets alter topography. As they grow, they raise the surface elevation. Higher elevation means lower temperature. This lapse rate effect means that an expanding ice sheet cools its own surface simply by becoming taller. This self-cooling makes it easier for ice to persist at its upper surface, even if surrounding regions experience some warming. It also encourages further snowfall, as cooler air holds less moisture and releases precipitation more readily when forced upward. Ice sheets also redirect atmospheric circulation. Cold, dense air tends to flow outward from their surfaces, creating persistent wind patterns that discourage warm air intrusion. This further isolates the ice from warming influences. Vegetation changes amplify these effects. As ice advances, it replaces forests and grasslands with barren or sparsely vegetated terrain. These surfaces are brighter and reflect more sunlight than vegetation-covered land. Even before ice arrives, tundra expansion increases albedo relative to forests. This means that climate cooling does not wait for ice to appear to begin reinforcing itself. The transition from forest to tundra already increases reflection and promotes cooling. Ice then builds upon that foundation. Clouds interact with albedo in complex ways. Clouds can reflect sunlight, cooling the surface, but they can also trap heat, warming it. In polar regions, low clouds often enhance cooling by reflecting sunlight during the brief summer. Changes in surface ice coverage influence cloud formation by altering temperature and moisture fluxes. As ice expanded during the early stages of cooling, cloud patterns likely shifted in ways that reinforced reflection during summer months. This further reduced the energy available to melt snow and ice. One of the most powerful aspects of albedo feedback is its persistence. Once ice becomes widespread, it does not disappear quickly even if temperatures rise modestly. The reflective surface reduces the effectiveness of warming influences, requiring stronger forcing to reverse the trend. This persistence explains why ice ages tend to last millions of years rather than thousands. Once reflection dominates large portions of the planet, the climate system becomes resistant to change. During the breakup of Pangea, albedo feedback gradually gained relevance as ice began to linger at the poles. At first, its influence was localized. Over time, it expanded, linking polar cooling to global climate. It is important to recognize that albedo feedback does not act alone. It works in concert with ocean circulation, atmospheric composition, and continental configuration. But among these factors, reflection is one of the most efficient amplifiers. Consider the planet's energy budget as a balance between incoming solar radiation and outgoing infrared radiation. Albedo directly affects the incoming side. By reducing how much energy enters the system, it shifts the entire balance toward cooling. This shift does not require changes in the sun or dramatic volcanic events. It can emerge purely from surface changes driven by tectonics and climate interactions. As continents moved and oceans widened, ice gained the opportunity to persist. Once it did, reflection began to shape the climate in a more decisive way. Each expansion of ice reduced absorbed energy. Each reduction in absorbed energy made further expansion easier. This is why early ice matters disproportionately. The first ice sets the stage. Later, ice builds upon an already altered energy landscape. Evidence for this process appears in geological records. Sedimentary deposits show increased ice-rafted debris in oceans, indicating the presence of floating ice. Isotope records show cooling trends consistent with expanding ice volume. Fossil distributions reflect changing climates that align with increased reflectivity. None of these records point to a sudden onset. They point to gradual accumulation. Reflection slowly gained influence until it could no longer be ignored. At this stage, Earth had entered a feedback-dominated regime. Cooling no longer required external nudges. The system could maintain and deepen cold on its own, provided the underlying geography continued to support it. That geography was still evolving. Continents were still drifting. Seaways were still opening and closing. Each change interacted with albedo feedback in subtle ways, sometimes strengthening it, sometimes limiting it locally, but overall allowing it to spread. Once ice albedo feedback becomes established at both poles, it can influence global temperature by altering the planet's average reflectivity. Even small increases in global albedo can produce measurable cooling. This cooling then influences carbon cycling. Cooler oceans absorb more carbon dioxide. Colder climates reduce chemical weathering in some regions while enhancing it in others. These changes further reduce greenhouse gas concentrations, reinforcing cooling. The result is a tightly coupled system where ice, reflection, and atmospheric composition work together. Breaking out of such a system requires substantial warming forces, which may not be available for long stretches of geological time. At this point in Earth's story, the power of reflection had transformed ice from a fragile seasonal feature into a durable climatic player. Ice was no longer merely responding to climate, it was shaping it. Yet even now, the planet was not fully locked into its coldest state. Reflection had tipped the balance, but other processes were still evolving. In particular, the movement of water through newly formed ocean pathways continued to change how heat was distributed globally. When ocean currents learn new routes, the planet does not notice immediately, but the climate always does. Currents are slow, patient systems. They do not rush. They do not react to short-lived changes. Instead, they respond to geography, gravity, and long-term energy balances. When continents move and seaways open or close, currents are forced to adapt, and in doing so, they quietly redefine where heat goes and where it does not. This process played a crucial role in turning tentative polar cooling into something far more persistent. To understand why new routes matter so much, it helps to remember that ocean currents are Earth's primary long-distance heat transport system. The atmosphere moves heat quickly, but it does not store much of it. Oceans move heat slowly, but they store vast amounts. Once heat enters the ocean, it can be carried across entire hemispheres and retained for centuries. When that transport changes, the climate response can last far longer than the initial trigger. During the time when Pangea was intact, ocean circulation was relatively simple on a global scale. A single massive ocean surrounded the supercontinent, and currents followed broad, continuous paths along its margins. Heat exchange between equator and poles was constrained by the shape of the land, but it was not fragmented by multiple basins and gateways the way it is today. As the supercontinent began to crack, narrow seaways appeared. At first, these passages were shallow and restricted. Water flowed through them slowly, sometimes intermittently. Even so, their existence introduced new possibilities. A current that had once been deflected now had an opening. A warm water mass that had been trapped could leak through. A cold current could extend farther than before. These early changes were modest, but they mattered because currents are sensitive to constraints. Remove a barrier, and the system reorganizes itself to find a more efficient path. That reorganization often produces winners and losers in terms of heat distribution. Some regions became warmer as new currents delivered heat more effectively. Others cooled as heat was diverted away. What matters for the Ice Age story is not global average temperature alone, but where cooling became persistent. High latitudes were among the first to feel the consequences. When currents that once delivered warmth toward the poles weakened or shifted, polar oceans cooled. Cooler oceans supported more sea ice. More sea ice increased albedo and reduced heat release into the atmosphere. These effects reinforced one another, making polar cooling more stable. One of the most important aspects of changing currents is the development of deep ocean circulation. Deep circulation depends on water density, which is controlled by temperature and salinity. Cold, salty water is dense and sinks. Warm or fresh water is lighter and stays near the surface. As continents separated and evaporation patterns changed, salinity gradients intensified. Some regions became saltier due to high evaporation and limited freshwater input. Others freshened due to increased rainfall or river discharge. These contrasts drove sinking in some areas and upwelling in others, establishing vertical circulation where little had existed before. Once cold water begins sinking in high latitudes, it spreads throughout the deep ocean. This cold, deep water can persist for centuries or longer, slowly influencing surface temperatures far from its source. In this way, localized polar cooling becomes a global background condition. New routes also allowed cold water to escape polar regions more efficiently. Instead of being trapped, it could spread equatorward along the seafloor, cooling deep ocean temperatures globally. Cooler deep oceans reduce the amount of heat that can be returned to the surface elsewhere, subtly lowering global temperatures. At the same time, warm equatorial currents were sometimes prevented from reaching higher latitudes due to continental barriers or altered pathways. When warm water fails to reach the poles, Polar regions rely more heavily on local solar input, which is already limited. This makes them especially vulnerable to cooling. These changes did not require large, modern-style ocean basins to be effective. Even relatively narrow seaways can redirect significant volumes of water over geological timescales. The key is persistence, not scale. Another important factor is the timing of current flow relative to seasons. Some currents deliver warmth during winter, which is especially effective at limiting ice growth. If those winter-warming currents weaken, ice gains an advantage even if summer conditions remain similar. Seasonal mismatches like this can be decisive. A small reduction in winter heat delivery can allow ice to thicken year after year, even if summers are only slightly cooler. Ocean currents play a disproportionate role in winter heat transport, making them central to ice stability. As currents adjusted, storm tracks adjusted as well. Storms often follow ocean temperature gradients. When currents shift, those gradients move. This can deprive polar regions of warm, moisture-bearing storms that would otherwise deliver heat. Instead, storms may track farther equatorward, leaving polar regions colder and drier. Dryness matters because dry cold favours ice preservation. Snow that falls in dry conditions tends to be lighter and more reflective. It also melts less efficiently without rain to accelerate melting. This further supports ice persistence. Ocean currents also influence cloud cover. Warm currents promote evaporation, which fuels cloud formation. Clouds can trap heat or reflect sunlight depending on conditions. When warm currents retreat, cloud patterns change, often allowing more heat to escape into space during winter nights. The cumulative effect of these adjustments is not sudden cooling, but a gradual narrowing of the range of conditions under which ice can melt. The climate system becomes biased toward cold retention. One of the most significant developments during this time was the increasing separation of ocean basins. As continents drifted apart, distinct basins began to form, each with its own circulation characteristics. These basins interacted, but not freely. Heat exchange between them became more complex and sometimes less efficient. This compartmentalization matters because it allows cold conditions to persist in one basin, even if others remain relatively warm. Global averages may mask these regional differences, but ice responds locally. As currents learned new routes, they also became more sensitive to small changes in geography. A slight narrowing of a passage could alter flow strength. A small shift in coastline could redirect a current. This sensitivity introduced variability, but also allowed certain configurations to lock in cooling. Evidence for these changes appears in marine sediments. Fossil assemblages show shifts in species adapted to cooler waters. Isotope data indicate changing water temperatures and circulation patterns. These signals align with the timing of continental separation and early polar cooling. Importantly, none of this required an external forcing like a change in solar output. The planet cooled because its internal plumbing changed. Water moved differently. Heat moved differently. The outcome followed naturally. As deep circulation strengthened, the ocean became more effective at storing cold. This storage dampened short-term warming events. Even if atmospheric conditions briefly favoured warmth, the cold ocean acted as a reservoir, pulling temperatures back down. This is another reason ice ages tend to be long-lived. Once the ocean fills with cold water, reversing that state requires sustained warming over very long periods. Brief warm intervals are insufficient. At this stage, the climate system had developed memory. Past cooling influenced future conditions. Ocean currents were the carriers of that memory, preserving cold long after its initial cause. The learning of new routes was not a one-time event. It continued as continents kept moving. Each new opening, each closure, each shift refined the circulation further. Some changes counteracted cooling locally, others reinforced it elsewhere. The overall trend, however, favoured increasing stability of cold at high latitudes. By now, ice was no longer a tentative feature. It was a participant in the system, interacting with currents in a feedback loop. Ice influenced currents by freshening surface waters as it melted seasonally. Currents influenced ice by delivering or withholding heat. The two became inseparable. This interdependence is crucial. It means that once cooling progressed beyond a certain point, no single process controlled the outcome. The system operated as a whole, with ocean circulation acting as both driver and stabilizer. As continents continued to separate, the potential for strong directional currents increased. Long, uninterrupted ocean passages allowed currents to accelerate and extend farther. These powerful flows could transport cold or warmth efficiently, depending on direction. When those currents favored cold transport, the reach of cooling expanded. Regions far from the poles began to feel its influence indirectly. Ocean temperatures lowered, atmospheric circulation adjusted, seasonal contrast sharpened. By this point, the groundwork for a full ice age had been laid. Ice had persistence, reflection had power, currents had memory. What remained was for these elements to synchronize more tightly. That synchronization would be aided by changes in atmospheric composition and volcanic activity, which influenced how much heat the planet retained overall. But the ocean's role remained central, because it determined how that retained heat was distributed. As the system evolved, cooling ceased to be a local whisper and became a planetary tendency. Not because the world froze overnight, but because water, once taught new routes, continued to follow them faithfully. Carbon, volcanoes, and a cooling sky are bound together in a relationship that unfolds far above the surface and far below it at the same time. It is a relationship that does not move quickly, does not respond to short-term fluctuations, and does not care about individual seasons. Instead, it reshapes climate over millions of years by quietly adjusting how much heat the planet is allowed to keep. During the long breakup of Pangea, this relationship shifted in ways that steadily favored cooling, even while dramatic geological activity was still unfolding. Carbon dioxide sits at the center of this story, because it is one of the most important regulators of Earth's temperature. It is not the only greenhouse gas, but over geological timescales, it is the most influential. Carbon dioxide absorbs infrared radiation emitted by Earth's surface and re-emits it, slowing the escape of heat into space. More carbon dioxide generally means a warmer planet. Less means a cooler one. The key word here is generally, because the carbon cycle is complex, slow, and deeply intertwined with tectonics. Volcanoes are one of the primary natural sources of carbon dioxide to the atmosphere. When magma rises and erupts, gases dissolved in it are released, including carbon dioxide. During periods of active rifting, volcanic activity increases. This might seem, at first glance, like a recipe for warming rather than cooling. Indeed, in the early stages of continental breakup, there were likely intervals of elevated atmospheric carbon dioxide and relative warmth. But this is only one side of the equation. Volcanoes add carbon quickly, but the processes that remove carbon operate continuously, and under certain conditions can outpace volcanic input. During the breakup of Pangea, those removal processes became increasingly effective. The most important of these processes is chemical weathering. When carbon dioxide dissolves in rainwater, it forms a weak acid. This acidic water reacts with silicate rocks on land, breaking them down and producing dissolved ions that rivers carry to the ocean. In the ocean, those ions eventually form carbonate minerals, locking carbon away in sediments for millions of years. Chemical weathering is slow, but it scales with surface area, temperature, and rainfall. As continents break apart, surface area increases. New coastlines appear. Fresh rock is exposed by tectonic uplift and volcanism. Rainfall patterns change, sometimes increasing over large areas. All of these factors accelerate weathering. Fresh volcanic rock is especially reactive. Basalt, the dark rock produced by many rift-related eruptions, weathers more quickly than older continental rocks. When large volcanic provinces form during continental breakup, they can draw down vast amounts of carbon dioxide over time, even if they initially release it. This creates a lagged response in the climate system. Volcanism may warm the planet briefly, but the long-term effect of enhanced weathering is cooling. The larger and more widespread the volcanic province is, the stronger this effect becomes. During the breakup of Pangea, volcanic activity was extensive but uneven. Massive lava flows covered large regions. Rift systems produced repeated eruptions. Over time, these rocks were exposed to rain, wind, and biological activity. The chemical reactions that followed steadily pulled carbon dioxide from the atmosphere. At the same time, the expansion of shallow seas and continental margins increased another important carbon sink: marine life. As oceans widened and new habitats formed, plankton populations expanded. These microscopic organisms use carbon dioxide for photosynthesis, building organic matter and shells. When they die, some of that carbon sinks to the seafloor and becomes buried. This biological pump operates continuously, but its efficiency depends on nutrient supply, circulation, and ocean chemistry. During continental breakup, rivers delivered increased nutrient loads to the oceans due to enhanced erosion. This fertilized marine ecosystems, boosting productivity and carbon burial. Buried carbon is effectively removed from the climate system for long periods. Once locked into sediments, it does not contribute to greenhouse warming unless it is later returned through tectonic processes. Over millions of years, even small increases in burial rates can significantly lower atmospheric carbon dioxide. While volcanoes continued to emit carbon, the balance between sources and sinks shifted. Weathering and burial increasingly matched or exceeded volcanic input. Atmospheric carbon dioxide began a long-term decline. This decline did not produce immediate or dramatic cooling. Instead, it lowered the planet's baseline temperature. Each degree of cooling made it easier for snow to survive. Each survival of snow strengthened albedo feedback. The system became progressively more receptive to ice. Volcanoes also influence climate in another way, through aerosols. Volcanic eruptions release sulfur dioxide, which can form sulfate aerosols in the atmosphere. These aerosols reflect sunlight, causing short-term cooling. On human timescales, this effect is temporary, lasting years rather than centuries. But during periods of frequent volcanism, these cooling pulses may have occurred repeatedly. Repeated aerosol-driven cooling does not create an ice age on its own, but it can assist other cooling mechanisms by tipping marginal regions over critical thresholds. A series of cooler summers can allow snow to persist long enough for albedo feedback to engage more strongly. Another important change involved the sky itself. As carbon dioxide levels declined, the atmosphere became more transparent to outgoing infrared radiation. Heat escaped more efficiently. Nights cooled more. Winters became harsher in regions already prone to cold. This effect is particularly strong in dry, high-latitude environments, where water vapour, another greenhouse gas, is less abundant. In such regions, carbon dioxide plays an outsized role in heat retention. Lowering its concentration disproportionately affects polar temperatures. Cloud behaviour also shifted as atmospheric composition changed. Cooler air holds less moisture. Reduced moisture can mean fewer clouds, especially in winter. Fewer clouds allow more heat to escape at night, reinforcing cooling. In summer, cloud changes can either enhance or reduce reflection, depending on cloud type and altitude. The net effect during this period likely favoured cooling at high latitudes. It is also important to consider how carbon cycling interacts with ocean circulation. Cooler oceans absorb more carbon dioxide from the atmosphere. As ocean temperatures dropped due to circulation changes, they drew additional carbon out of the air, reinforcing the decline in atmospheric greenhouse gas concentrations. This oceanic uptake acts as a stabilizer for cooling. Once temperatures fall, the ocean responds by absorbing more carbon dioxide, which further reduces warming potential. Reversing this process requires significant warming to release carbon back into the atmosphere. The combined effect of enhanced weathering, increased biological burial, and cooler oceans created a powerful downward pressure on atmospheric carbon dioxide. Volcanoes continued to add carbon, but the system had shifted into a state where removal processes dominated over geological timescales. The sky, in response, became less effective at trapping heat. This does not mean the planet became cold everywhere. Tropical regions remained warm, but temperature gradients sharpened. The difference between equator and poles increased. Stronger gradients intensified certain wind systems, while weakening others, further influencing heat transport. At the poles, these changes were decisive. Lower greenhouse gas concentrations reduced the warmth retained during long polar nights. Ice that had begun to persist seasonally now found it easier to survive year after year. Snowfall that once melted completely began to accumulate. This accumulation did not proceed smoothly. There were pauses, reversals, and fluctuations. But the overall direction favoured ice stability. Each fluctuation occurred around a cooler average than before. One of the most important aspects of carbon-driven cooling is its inertia. Carbon cycles operate slowly. Once atmospheric carbon dioxide declines significantly, it does not rebound quickly unless volcanic activity increases dramatically or weathering slows. During the continued breakup of Pangea, neither of those conditions consistently favoured rapid warming. In fact, as continents spread apart, mountain building associated with collisions and rifting continued to expose fresh rock, maintaining high weathering rates. Rivers continued delivering carbon to the oceans. Biological systems adapted to cooler conditions, sustaining carbon burial. This long-term cooling pressure worked hand in hand with the physical feedbacks already in place. Ice reflected sunlight. Oceans redistributed cold. Winds isolated polar regions. Carbon reduction lowered the thermal ceiling. None of these processes alone would necessarily produce a full ice age. Together, they created a system biased toward cold persistence. The cooling sky was not the result of a single volcanic lull or a sudden atmospheric change. It was the cumulative outcome of a planet rearranging its surface and, in doing so, altering its chemistry. Earth was not losing heat because something external had changed. It was losing heat because it had become better at letting heat go. Seasons that grow sharper, winters that linger, do not emerge from a single cause. They are the outcome of many slow adjustments aligning in the same direction, each one small enough to seem harmless on its own, yet powerful when combined over long stretches of time. As the planet cooled gradually during the breakup of Pangea, the balance between summer and winter began to shift. Not dramatically at first, but persistently. The rhythm of the year itself started to change. Seasonality exists because Earth is tilted. That tilt determines how sunlight is distributed across the planet throughout the year. But how strongly seasons are felt depends on geography, atmospheric composition, ocean circulation, and surface conditions. When those factors change, the same tilt can produce very different outcomes. As continents moved and oceans widened, heat became less evenly distributed. Summers in some regions became slightly cooler. Winters in those same regions became slightly colder. This asymmetry mattered. Ice responds far more to summer weakness than to winter strength. A colder winter alone does not guarantee ice growth if summer warmth is sufficient to erase it. But when summers lose their ability to fully melt snow and ice, winter gains accumulate. During the early stages of cooling, summers did not suddenly become cold. They simply became less effective. Snow lingered longer into the warm season. Melt season shortened by small increments. In polar and near-polar regions, this was enough to allow snowpack to survive year after year in protected areas. At the same time, winters began extending their influence. Colder oceans released less heat into the atmosphere. Reduced greenhouse gas concentrations allowed heat to escape more efficiently at night. Snow-covered land reflected sunlight during the short winter days, preventing even modest warming. Cold air pooled over ice and tundra, deepening winter chill. This growing imbalance between summer and winter gradually sharpened seasonal contrasts. Winters became more dominant, summers became less decisive. The calendar did not change, but the climate's response to it did. Continental interiors experienced this sharpening especially strongly. As land masses fragmented, some interior regions shrank, while others remained extensive. Where large land areas persisted at higher latitudes, seasonal extremes intensified. Land cools and warms more quickly than ocean. Without nearby water to moderate temperature swings, winters grew harsher. Meanwhile, coastal regions experienced a different kind of seasonal shift. Oceans moderated temperatures, but as currents changed, that moderation sometimes favoured cold persistence over warmth delivery. In some places, cool summers replaced mild ones. In others, long damp winters replaced shorter cold spells. Snowfall patterns adjusted accordingly. Sharper seasons often mean more intense precipitation during certain periods. When winter storms delivered heavy snowfall and summers failed to fully melt it, accumulation followed. Snowlines descended gradually, not because snowfall increased dramatically, but because melt decreased. Orbital variations also played a role, even though they operate independently of continental drift. Earth's orbit and axial tilt change over tens of thousands of years, affecting the intensity of seasons. When orbital configurations reduced summer sunlight in high latitudes, they amplified the cooling trends already in place. These orbital cycles alone do not cause ice ages, but when the climate system is already predisposed toward cold, they can trigger significant ice growth. During the breakup of Pangea, the system was becoming increasingly sensitive to these cycles. In such a sensitive state, a slightly weaker summer, due to orbital alignment, could have a much larger impact than it would have in a warmer world. Ice that might once have melted now survived. Each survival event strengthened albedo feedback, reinforcing cooling. Winters that linger are not just colder winters. They are winters that extend their influence into spring and autumn. Snow persists later into spring, delaying warming. Early snowfall arrives sooner in autumn, shortening the effective warm season. This compression of summer further limits main, ensures ice advantage. Vegetation responded to these changes in ways that reinforced seasonality. Shorter growing seasons favoured hardy, low-growing plants over forests. Tundra expanded, grasslands shifted. These landscapes reflected more sunlight and trapped snow more effectively, deepening winter dominance. Animal life adapted as well. Migration patterns shifted. Hibernation strategies evolved. Species ranges moved equatorward or toward lower elevations. These biological adjustments did not drive climate change directly, but they influenced carbon storage and surface reflectivity, feeding back into the system. Atmospheric circulation reflected these changes. Stronger temperature gradients between seasons intensified some wind systems while weakening others. Persistent winter high-pressure systems became more common in cold regions, trapping cold air and discouraging storm intrusion that could bring warmth. Storm tracks shifted as well. Some regions experienced fewer winter storms, leading to drier cold that favoured snow preservation. Others experienced more intense snowfall events, contributing to ice buildup. Both scenarios supported long-term cooling when summers were weak. As winters lingered, permafrost expanded. Frozen ground altered hydrology, reducing infiltration and increasing runoff during brief melt periods. This affected erosion patterns and nutrient delivery to oceans, subtly influencing carbon cycling. Longer winters also increased sea ice duration. Sea ice formed earlier and melted later, expanding its average extent. This further reduced ocean-atmosphere heat exchange and increased albedo, reinforcing cooling. Importantly, these changes did not occur uniformly across the globe. Tropical regions remained relatively stable. Mid-latitudes experienced complex shifts. The focus remained on high latitudes, where small seasonal changes had the greatest impact. Over millions of years, the cumulative effect of sharper seasons was profound. Ice no longer needed extraordinary conditions to grow. It needed only consistency. Winters provided accumulation. Summers failed to erase it. Feedbacks did the rest. By this stage, the climate system had crossed into a regime where Ice Age conditions were no longer unlikely. They were plausible, not inevitable yet, but increasingly favoured. This does not mean the planet was locked into permanent cold. Warm intervals still occurred. But each warm interval had to overcome a stronger seasonal imbalance. Each cooling phase had an easier path to persistence. As seasons grew sharper and winters lingered, the stage was set for ice to expand beyond isolated patches. What had begun as whispers at the poles now had the structural support to spread. Life learns to shiver, adapt, or wander not because it senses an ice age approaching, but because the rules of survival quietly change beneath it. No organism understands continental drift or carbon cycles. What life responds to are shorter summers, longer winters, shifting rainfall, cooling oceans, and landscapes that no longer behave the way they once did. As the planet continued cooling during and after the breakup of Pangea, these subtle environmental changes accumulated until they reshaped ecosystems across land and sea. At first, the changes were easy to absorb. Many species already lived with seasonal variability. Cold snaps, dry years, and regional climate differences were nothing new. But as cooling became more persistent, variability gave way to trend. The average year began to look different from the one before it. Winters bit a little harder. Summers offered a little less relief. Over thousands of generations, that difference mattered. Plants were often the first to respond because they are rooted in place. They cannot migrate quickly. Instead, they adapt physiologically or disappear from regions that no longer suit them. As temperatures dropped and growing seasons shortened, plants that relied on long, warm summers struggled. Trees that once thrived at higher latitudes found it harder to complete their growth cycles. Frost damage became more frequent. Seed production declined. Gradually, forests retreated toward lower latitudes and lower elevations. In their place, more cold-tolerant vegetation expanded. Shrubs, grasses, and low-growing plants with shorter life cycles gained an advantage. These plants could complete their growth during brief summers and survive long winters in dormant states. This shift mattered for climate as well. Forests absorb sunlight efficiently. Grasslands and tundra reflect more of it. As vegetation changed, surface reflectivity increased, reinforcing cooling. Life was not just responding to climate, it was shaping it, unintentionally but effectively. Soils changed too. Cooler temperatures slowed decomposition. Organic matter accumulated in some regions, while frozen ground limited nutrient cycling in others. Permafrost expanded, locking away carbon and altering hydrology. Wetlands formed in some places as drainage patterns changed, while others dried out under persistent cold and reduced evaporation. Animals responded in different ways depending on their mobility. Small organisms with short life cycles adapted genetically over relatively short timescales. Changes in body size, fur density, metabolic rates, and reproductive timing appeared gradually. Cold tolerance became a valuable trait. Larger animals faced a different set of options. Adaptation was possible, but slow. Migration offered a more immediate solution. As climates shifted, many species tracked their preferred conditions across the landscape. Ranges moved equatorward. Elevational migrations became more common. Animals followed retreating vegetation zones, maintaining access to food and suitable temperatures. Because continents were still partially connected during much of this period, migration routes were extensive. There were few ocean barriers early on. This allowed species to move long distances without crossing water, reducing extinction pressure compared to later periods when continents were fully separated. Even so, not all species could keep up. Those with narrow ecological niches struggled. Specialists that relied on specific food sources or climate conditions found themselves squeezed as environments transformed. Some adapted, others declined and vanished from certain regions. Marine life experienced parallel changes. Cooling oceans altered nutrient distribution and circulation. Species adapted to warm waters retreated toward the equator. Cold-tolerant species expanded their ranges poleward. Plankton communities shifted, affecting entire food webs. These marine changes had important climate implications. Different plankton species sequester carbon at different rates. As cold-adapted plankton became more common, patterns of carbon burial shifted. This influenced atmospheric carbon dioxide levels, reinforcing cooling trends. Coral reefs, which require warm, stable conditions, contracted significantly. Their decline reduced carbonate production in some regions, subtly altering ocean chemistry. Meanwhile, cold water ecosystems expanded, supporting different types of organisms adapted to low temperatures and seasonal productivity. Life in polar regions faced the greatest challenges. As ice persisted longer, habitats became fragmented. Open land gave way to snow-covered terrain. Food availability became seasonal and unpredictable. Survival favoured flexibility. Some animals evolved thick insulating coverings. Others developed behaviours like hibernation, reducing energy needs during harsh winters. Still others relied on migration, leaving polar regions entirely during the coldest months. Birds likely played a key role during this period. Flight allowed rapid response to changing seasons. Migration patterns could shift quickly, tracking food availability across continents. These patterns became increasingly important as seasonal contrasts sharpened. Insects responded by adjusting life cycles. Shorter summers favoured rapid development. Many species synchronized reproduction with brief warm periods, entering dormant states for much of the year. This synchronization reduced exposure to lethal cold. Aquatic organisms in freshwater systems also adapted. Lakes and rivers froze more consistently. Ice cover altered oxygen availability and light penetration. Species adapted to these conditions or retreated to refugia where water remained unfrozen. What is striking about this phase is not widespread extinction, but widespread adjustment. Life proved remarkably resilient. The planet did not suddenly become uninhabitable. Instead, it became more selective. Selective pressure increased. Traits that had once been neutral or mildly beneficial became critical. Cold tolerance, flexible diet, mobility, and efficient energy use were favoured. Over time, these pressures reshaped populations. Evolution operates continuously, but it accelerates under stress. Cooling climates provided that stress. Genetic diversity became a resource. Populations with greater variability had more options. Those without it faced decline. Importantly, these changes occurred against a backdrop of ongoing continental movement. As land masses continued drifting, new barriers eventually formed. Oceans widened. Migration routes narrowed. This increased isolation in later stages, raising extinction risks. But during the early and middle phases of cooling, connectivity still allowed many species to respond by moving rather than disappearing. This delayed the most dramatic biological consequences, even as climate trends continued. Life also influenced erosion and weathering. Vegetation stabilizes soil. As forests retreated, erosion increased in some regions. Increased erosion exposed fresh rock, accelerating chemical weathering and carbon removal. This is another example of biological response feeding back into climate. In cold regions, reduced vegetation allowed wind to transport dust more easily. Dust deposition affected snow albedo, cloud formation, and nutrient delivery to oceans. These processes further intertwined biological and physical systems. Humans, of course, were not present during this time. But understanding how life responded then helps explain how ecosystems behave under gradual climate stress more generally. Life does not collapse instantly. It reorganizes. As cooling progressed, ecosystems entered a state of constant adjustment. boundaries between biomes shifted repeatedly. Forests advanced and retreated. Grasslands expanded and contracted. Tundra appeared, disappeared, and reappeared in different regions as conditions fluctuated around a cooler average. This dynamic state persisted for millions of years. It was not a frozen world, but a restless one. Ice was becoming more common, but it did not yet dominate landscapes everywhere. Life still had room to move. The concept of wandering is particularly important here. Migration is not failure, it is strategy. Many species survived cooling not by adapting physiologically, but by relocating. This mobility allowed life to persist even as environments transformed. Eventually, however, as ice expanded and continents separated further, wandering became more constrained. That is when adaptation and extinction pressures intensified. But during this stage, movement was still an effective response. As life learned to shiver, adapt, or wander, it shaped the planet in return. Vegetation changes altered reflectivity. Marine ecosystems influenced carbon cycling. Animals redistributed nutrients. None of this was intentional, but all of it mattered. By this point, cooling was no longer confined to the poles. Its influence extended into mid-latitudes through shifting ecosystems and atmospheric circulation. The world was not yet locked into its coldest state, but it was firmly on a path where ice was becoming a reliable presence. Snowball Earth or gentle freeze is not a question about extremes versus moderation, so much as it is a question about balance. It asks whether a planet drifting toward cold must inevitably plunge into a near-total deep freeze, or whether it can settle into a long, stable state of partial ice without losing its ability to support diverse life. During the cooling that followed the breakup of Pangea, Earth hovered between these possibilities. The difference lay not in a single mechanism, but in how many competing forces leaned in one direction versus the other. To understand this tension, it helps to clarify what a snowball Earth actually is. A true snowball Earth refers to a state in which ice covers nearly the entire planet, from poles to equator. Oceans freeze over, land disappears beneath ice sheets, and surface temperatures remain far below freezing for millions of years. Geological evidence suggests this happened at least twice very early in Earth's history, long before complex life existed. A gentle freeze, by contrast, is a world with permanent ice at the poles, extensive glaciers, and recurring ice ages, but also with open oceans, ice-free tropics, and habitable mid-latitudes. This is the kind of world Earth has occupied for much of the last several 100 million years. Ice is influential but not all-consuming. As Earth cooled during and after Pangea's breakup, it did not start from a neutral position. It carried with it a history. Earlier snowball Earth events had occurred under very different conditions. When the sun was dimmer, atmospheric composition was different, and continental arrangements were unlike anything that followed. By the time Pangea existed, Earth had already developed stabilizing mechanisms that made a full snowball less likely. One of the most important stabilizers was the carbon cycle. While declining carbon dioxide favored cooling, it also created a self-limiting mechanism. As temperatures drop and ice expands, chemical weathering slows dramatically. Frozen ground limits water-rock interactions. Reduced rainfall limits carbon drawdown. This slowdown allows volcanic carbon dioxide emissions to rebuild atmospheric concentrations over time. In a snowball Earth scenario, this process is extreme. Weathering nearly halts under global ice cover. Volcanoes continue emitting carbon dioxide beneath the ice. Over millions of years, carbon dioxide accumulates until greenhouse warming becomes strong enough to melt the ice catastrophically. This is how Earth escaped past snowball states. During the cooling associated with Pangea's breakup, Earth never fully shut down weathering. Ice expanded, but large ice-free regions remained. Rivers still flowed, rain still fell. Carbon drawdown continued, but it did not collapse entirely. This allowed the system to hover in a cooler equilibrium rather than tipping fully into a snowball. Ocean circulation also played a moderating role. In a snowball Earth, ocean circulation weakens dramatically as ice covers the surface and limits interaction with the atmosphere. Heat transport becomes minimal. In the Pangea-related cooling, oceans remained active. Currents continued redistributing heat, even if their patterns favoured cooling at the poles. This active circulation prevented complete thermal isolation between equator and poles. Warmth still reached low and mid-latitudes reliably. Ice struggled to advance beyond certain boundaries because summer melting remained effective in those regions. Another key factor was the distribution of continents. During snowball Earth events, continental arrangements likely favoured ice expansion across low latitudes. Large land masses near the equator provided surfaces where ice could accumulate and persist. During and after Pangea's breakup, continents gradually moved into configurations that left much of the equator ocean-dominated. Open tropical oceans absorb heat efficiently and resist freezing. They act as thermal anchors, maintaining warm conditions even when polar regions cool dramatically. As long as these warm anchors exist, global ice cover becomes difficult to achieve. The sun itself was also brighter during Pangea's breakup than during earlier snowball Earth periods. Solar luminosity increases slowly over geological time. By the time of Pangea, the sun delivered significantly more energy to Earth than it had during ancient snowball episodes. This additional energy raised the threshold required for global freezing. Albedo feedback, while powerful, also has limits. As ice expands toward lower latitudes, it encounters stronger sunlight. Reflection remains effective, but incoming energy increases. At some point, melting balances accumulation. This balance point defines the boundary between gentle freeze and runaway snowball. During the cooling we're examining, that balance point was reached before ice could overtake the tropics. Ice sheets expanded. Sea ice grew. Glaciers advanced. But they stalled where summer sunlight and ocean heat transport became sufficient to counter further spread. Life itself contributed to this moderation. Biological activity affects atmospheric composition in ways that can stabilize climate. Even simple ecosystems influence carbon cycling, cloud formation, and surface reflectivity. During snowball Earth events, life was sparse and mostly microbial. During Pangea's breakup, life was abundant and complex. Vegetation, even tundra, darkens the surface relative to pure ice. Forests and grasslands absorb sunlight and moderate temperature locally. Marine life influences carbon storage and nutrient cycling. These biological processes add friction to climate extremes. Another stabilizing factor involved water vapor. While water vapor is a greenhouse gas, its distribution depends on temperature. In a snowball Earth, cold air holds little moisture, reducing greenhouse trapping. During a gentle freeze, warmer regions still produce water vapor, enhancing heat retention and preventing runaway cooling. Cloud feedbacks also differ between the two scenarios. In a snowball Earth, cloud formation is limited by cold and dryness. In a partially ice-covered world, clouds remain abundant in warmer regions, reflecting sunlight but also trapping heat, depending on conditions. These mixed effects further resist uniform global freezing. Ice dynamics themselves impose limits. Ice sheets flow under their own weight. As they thicken, they spread outward, but they also carve, melt at edges, and respond to basal heat from the earth below. Complete coverage requires conditions that suppress all these loss mechanisms simultaneously, which is difficult outside of exceptional circumstances. During the cooling associated with continental breakup, ice loss processes remained active. Glaciers advanced and retreated. Sea ice expanded seasonally and contracted. Ice sheets thickened but also experienced melting at margins. The system oscillated rather than locking. Geological records reflect this oscillation. Sediments show alternating layers indicative of glacial and interglacial conditions. Fossil assemblages point to repeated expansions and contractions of cold-adapted ecosystems. These patterns are inconsistent with a true snowball state, but align well with a prolonged gentle freeze punctuated by fluctuations. This does not mean the climate was mild, it was often harsh. Large regions experienced persistent cold. Sea levels fluctuated as ice volume changed. Ecosystems were stressed. But the planet retained flexibility. The difference between snowball Earth and gentle freeze is ultimately a difference in resilience. A snowball state overwhelms, the system stabilizes. A gentle freeze engages them. During Pangea's breakup, cooling forces were strong but not overwhelming. Continental rearrangement, ocean circulation changes, albedo feedback, and carbon drawdown all push toward cold. At the same time, solar input, ocean heat storage, biological activity, and carbon cycle feedbacks pushed back. The result was not a dramatic plunge into global ice, but a drawn-out negotiation. Ice gained ground, then lost some. It advanced again under favourable conditions, then retreated partially. Over millions of years, this negotiation settled into a pattern of recurring ice ages rather than permanent ice cover. This pattern is significant because it defines the climate regime Earth still occupies today. We live on a planet that has ice at the poles, seasonal snow at high latitudes, and a climate system capable of swinging between colder and warmer states without collapsing entirely. The gentle freeze model also explains why ice ages tend to come in cycles rather than as single unbroken events. Once the planet enters a cool regime, orbital variations, volcanic fluctuations, and biological changes can trigger repeated advances and retreats of ice, without fundamentally altering the baseline state. In this sense, the breakup of Pangea may not have triggered a single ice age, but it helped establish the conditions under which ice ages became a recurring feature of Earth's climate. It shifted the planet from a largely ice-resistant configuration to one where ice could appear repeatedly and persist for long periods. This perspective helps reconcile the evidence. We see extensive glaciation following continental breakup, but we do not see a return to snowball Earth conditions. The planet cooled, but it did not freeze solid. Understanding why Earth avoided a full snowball during this time also helps scientists assess climate stability more broadly. It shows that multiple stabilizing mechanisms operate simultaneously, and that extreme outcomes require not just strong forcing, but the absence or failure of those stabilizers. As continents continued drifting toward their modern positions, the balance continued to evolve. Some stabilizers weakened, others strengthened. The climate system remained dynamic. What the rocks remember that we forgot is not a metaphor about memory in the human sense, but a statement about persistence. Rocks do not forget because they do not need to. They record. They accumulate evidence quietly, layer by layer, grain by grain, long after oceans have shifted, climates have cooled, and continents have wandered far from their original positions. When scientists try to understand whether the breakup of Pangea nudged the planet toward an ice age, they're not relying on guesswork or imagination alone. They are reading what the rocks have been preserving all along. The surface of Earth is constantly changing, but not everything is erased. Erosion removes some traces, but burial preserves others. Sediments settle, minerals crystallize, fossils embed, and chemical signatures lock into place. Over millions of years, these processes create a geological archive far more reliable than any written record could ever be. The challenge is not whether the record exists, but whether we know how to interpret it. One of the most direct ways rocks reveal past cold is through glacial deposits. When ice moves across land, it leaves behind unmistakable signatures. Scratches carved into bedrock show the direction of ice flow. Poorly sorted sediments, known as till, accumulate beneath glaciers and contain a chaotic mix of particle sizes that water alone cannot produce. Large boulders, transported far from their source and dropped when ice melts, sit stranded in landscapes where they do not belong. These features are found across multiple continents in rocks that date to periods following the breakup of Pangea. They appear not as a single global layer, but as regionally distributed evidence that ice existed in places where today it does not. This scattered pattern fits a world experiencing prolonged, variable glaciation rather than a uniform global freeze. Marine sediments tell a complementary story. As ice grows on land, sea level falls because water is locked away in ice sheets. When ice retreats, sea level rises. These changes leave clear marks in sedimentary layers along ancient coastlines. Sequences of shallow water deposits alternating with deeper water sediments indicate repeated advances and retreats of ice over long periods. Within these marine layers, scientists find ice-rafted debris. These are fragments of rock that could only have been transported by floating ice. As icebergs break off glaciers and drift into the ocean, they carry debris. When the ice melts, the debris sinks and settles onto the sea floor. Finding such material far from any ancient shoreline is strong evidence of glacial activity. Chemical signatures within rocks provide another powerful line of evidence. Oxygen isotopes, particularly the ratio of oxygen 18 to oxygen 16, are sensitive to temperature and ice volume. When ice sheets grow, they preferentially trap lighter oxygen isotopes, leaving the ocean enriched in heavier ones. Marine organisms incorporate this oxygen into their shells, preserving a record of global ice volume and temperature at the time they lived. Across rock layers corresponding to the long cooling following Pangea's breakup, these isotope ratios shift gradually toward values associated with cooler conditions and increased ice storage. The change is not abrupt. It unfolds slowly, reinforcing the idea of a gentle but persistent transition rather than a sudden climatic collapse. Carbon isotopes add another layer to the story. Changes in the carbon cycle, driven by weathering, biological activity, and ocean circulation, leave distinct signatures in carbonate rocks and organic sediments. Periods of increased carbon burial correspond to declining atmospheric carbon dioxide and cooling climates. These patterns appear repeatedly in the geological record during the time when continents were separating and oceans were reorganizing. Volcanic rocks also preserve important clues. The timing and distribution of large igneous provinces associated with continental rifting are well documented. These rocks show when and where volcanic activity released carbon dioxide into the atmosphere. When compared with climate proxies, they reveal the lag between volcanic emissions and subsequent cooling driven by enhanced weathering of fresh rock. This lag is critical. It explains why warming and cooling can occur in close proximity in the geological record without contradicting one another. Volcanoes warm the planet briefly. Weathering cools it over longer timescales. Rocks capture both signals, allowing scientists to reconstruct the sequence rather than seeing only the outcome. Fossils, too, are part of the archive. The distribution of plant and animal fossils reflects the climates in which those organisms lived. Cold-adapted species appear in higher latitudes and elevations over time. Warm-adapted species retreat or disappear from regions that become too cold. These shifts align with other evidence of cooling and ice expansion. Pollen preserved in sediments provides especially fine detail. Different plant species produce distinct pollen grains that are resistant to decay. By analysing pollen assemblages layer by layer, scientists can reconstruct vegetation changes with remarkable precision. These records show forests giving way to grasslands and tundra as climates cooled and seasons sharpened. Soils, often overlooked, also tell a story. Ancient soils preserved beneath volcanic layers or within sedimentary sequences reveal information about temperature, rainfall, and vegetation. Certain soil types form only under specific climate conditions. Their presence or absence helps constrain past environments. Even the orientation of magnetic minerals in rocks contributes. As lava cools or sediments settle, magnetic minerals align with Earth's magnetic field. This provides information about the latitude at which the rock formed. By combining paleomagnetic data with climate indicators, scientists can determine whether cold conditions occurred at expected latitudes or extended unusually far toward the equator. What emerges from all these lines of evidence is not a single dramatic moment. but a coherent pattern. Cooling follows continental breakup. Ice appears first at the poles and high elevations. Glaciation becomes more widespread but remains variable. Warm intervals punctuate the record, but they occur against a progressively cooler baseline. This pattern would be difficult to explain without invoking changes in geography, ocean circulation, and atmospheric composition. Rocks do not suggest an external catastrophe or sudden solar dimming. They point to Earth responding to its own rearrangement. The reason this record feels forgotten is not because it was lost, but because human timescales make it difficult to intuit. Millions of years compress into thin layers of stone. What feels like a static cliff face is actually a detailed chronicle of change. Modern landscapes often obscure these records. Erosion removes some evidence, tectonics buries or distorts others. But enough remains to piece together the story. And when rocks from different continents tell similar stories at similar times, confidence grows. It is also worth noting what the rocks do not show. They do not show evidence of a full snowball Earth during this period. There are no global glacial deposits at low latitudes of the same age. There are no signs of complete ocean freezing. Instead, the record consistently points to partial, persistent glaciation. This absence is just as informative as the presence of ice. It reinforces the idea that Earth entered a new climate regime without overshooting into total freeze. The stabilizing mechanisms discussed earlier left their mark by limiting how far ice could spread. The rocks also reveal timing. Cooling did not begin exactly when Pangea started to crack. There was a delay. That delay reflects the time required for feedbacks to build. Geography changed first, oceans followed, carbon cycles adjusted, ice responded last. This sequence matters because it shows causality. Ice was not the driver, it was the outcome. The planet's structure set the stage long before ice took centre stage. In some regions, the record is especially clear. Southern continents that once formed part of Gondwana preserve extensive glacial deposits from this era. These deposits align with reconstructions showing those land masses drifting into higher latitudes. The coincidence of movement and ice is difficult to ignore. Northern regions show similar patterns, though often modified by later tectonic events. Where rocks survive, they tell the same story. Ice followed geography. What the rocks remember then is not just that Earth cooled, but how it cooled. Slowly, unevenly, persistently. They remember the order of events even when surface appearances suggest otherwise. This memory is crucial because it challenges simplistic narratives. Ice ages are often imagined as sudden or externally imposed. The geological record argues otherwise. It suggests that Earth climate is deeply self-organizing, capable of drifting to new states through internal reconfiguration. Understanding this helps place modern climate change in context. While the timescales are very different, the principle that geography, circulation and chemistry shape climate remains true. Rocks remind us that climate is not fixed, but neither is it chaotic. It follows rules, even if they operate slowly. As continents continue to move after Pangea's breakup, the geological record continued to accumulate. New ice advances left new marks, new warm periods left others. The archive grew richer. Eventually, those continents reached configurations closer to what we recognize today. At that point, the climate system entered a phase that feels more familiar, with recurring ice ages driven by orbital cycles rather than tectonic upheaval. Could it happen again on a restless planet is not a question meant to provoke fear or prediction, but one meant to invite perspective. It asks whether the same slow forces that once guided Earth into a long era of cold are still capable of doing so, given enough time, movement, and patience. To explore this, it is necessary to step away from the dramatic imagery often associated with ice ages, and instead focus on the underlying mechanics that made them possible in the first place. Earth has never been still. The surface we experience as solid and dependable is, on geological timescales, flexible and mobile. Continents drift, oceans open and close, mountains rise and erode. The processes that broke Pangea apart did not end when the supercontinent disappeared. They continue today, just as quietly, just as persistently. Tectonic plates are still moving at roughly the same rates they always have, a few centimetres per year. That speed feels insignificant in a human lifetime, but over millions of years it is transformative. Entire oceans can open or vanish. Continents can migrate from equator to pole. These movements remain fully capable of reshaping climate, not through sudden change, but through gradual reorganization. One of the most important lessons from the breakup of Pangea is that climate does not respond to tectonics immediately. There is always a delay. Geography changes first, circulation adjusts next, chemistry follows, ice responds last. This lag is crucial when considering whether similar cooling could happen again. Today's continents are arranged in a way that strongly influences ocean circulation. The presence of a nearly continuous ring of ocean around Antarctica, for example, allows cold currents to circulate freely, isolating the continent and supporting permanent ice sheets. This configuration did not exist for most of Earth's history. It formed only when southern land masses drifted apart sufficiently. If continental movement were to disrupt such configurations in the future, the climate consequences would be significant. Closing or opening ocean gateways can alter heat transport dramatically. A land bridge forming where open ocean once existed could redirect currents, delivering warmth to regions that are currently cold or depriving others of heat they now receive. The same is true in reverse. If new passages open or widen, currents can strengthen or shift in ways that favour cooling. There is nothing in Earth's tectonic behaviour that prevents such rearrangements from happening again. They are not hypothetical, they are ongoing. Another key factor is continental position relative to the poles. Ice sheets form most easily on land at high latitudes. Today, Antarctica occupies the South Pole, providing an ideal platform for ice accumulation. In the Northern Hemisphere, large land masses also extend into high latitudes, allowing seasonal snow and ice to persist. If continental drift were to move major land masses away from polar regions over tens of millions of years, ice formation would become more difficult. Conversely, if land were to migrate toward the poles, the potential for long-term ice accumulation would increase. Earth has experienced both scenarios in the past. The planet alternates between ice-friendly and ice-resistant configurations, depending on where continents happen to be. There is no permanent state. Carbon cycling remains another critical consideration. Over geological timescales, atmospheric carbon dioxide is regulated primarily by the balance between volcanic emissions and chemical weathering. That balance is sensitive to tectonics. Mountain building increases weathering. Rifting exposes fresh rock. Continental arrangement influences rainfall patterns. If future tectonic activity were to enhance weathering significantly without a corresponding increase in volcanic emissions, atmospheric carbon dioxide could decline over millions of years, favouring cooling. This is exactly the pattern observed during the breakup of Pangea. Conversely, if volcanic emissions dominate, warming could prevail. The system is dynamic, not predetermined. It responds to the relative strength of competing processes. Solar output also plays a role, but not in the way it is often imagined. The sun grows brighter over time, increasing the amount of energy Earth receives. This gradual brightening raises the threshold required for global cooling. In other words, future ice ages driven purely by tectonics would need stronger cooling mechanisms than those in the distant past. However, this does not eliminate the possibility of ice, it merely changes the balance point. Partial glaciation, polar ice, and recurring ice ages remain possible even under a brighter sun, provided other conditions align. Ocean circulation remains central to this alignment. The modern global conveyor belt moves heat efficiently, but it is sensitive to geography. Changes in salinity, temperature, or basin connectivity can weaken or redirect circulation. Such changes have occurred many times before and will occur again. The memory stored in deep ocean water, discussed earlier, still exists. Oceans can retain cold for long periods, influencing climate long after initial conditions change. This inertia means that once cooling begins, it can persist even if the original trigger weakens. Albedo feedback remains just as powerful as it ever was. Ice and snow still reflect sunlight. Vegetation changes still influence reflectivity. These feedbacks do not depend on ancient conditions. They operate today exactly as they did in the past. The difference lies in timescale. The processes that once nudged Earth toward an ice age operated over tens of millions of years. Human-induced climate change operates over centuries. These are not comparable in speed or mechanism. Asking whether an ice age could happen again is not the same as asking whether one is imminent. In the near future, tectonics will not counteract human-driven warming. Plate movement is far too slow. Carbon cycle adjustments driven by weathering take millions of years. The climate changes we are currently experiencing unfold on timescales that geology cannot match. But over deep time, beyond human horizons, Earth remains capable of dramatic climate shifts driven by its own internal processes. There is nothing in the planet's behaviour that suggests it has settled into a permanent climate state. Future supercontinents are likely to form. Models of plate motion suggest that continents may eventually merge again, creating new configurations unlike anything today. Those future arrangements will reshape ocean circulation, wind patterns, and carbon cycling in ways we cannot predict in detail, but whose general effects we understand. If a future supercontinent were to form near the equator, it could favour warmth and reduce ice. If it formed spanning the poles, it could favour cold. If it fragmented in a way similar to Pangea, it could again tip the climate toward a long era of glaciation. The planet does not remember past ice ages in a way that prevents new ones. There is no learning or avoidance. The same rules apply each time. Geometry, chemistry, and physics interact, and the outcome depends on their balance. What does change is life. Each ice age occurs in a different biological context. The cooling following Pangea's breakup occurred in a world without humans. Future cooling, if it occurs millions of years from now, will unfold in a world shaped by whatever life exists then. Life influences climate, but it does not control tectonics. It responds, adapts, migrates, and sometimes disappears. This pattern too has not changed. The question of whether it could happen again is therefore best answered with caution and humility. Yes, the mechanisms still exist. Yes, Earth remains restless. But the timing, sequence, and expression of future cooling will be unique, shaped by conditions we cannot yet fully imagine. Importantly, the past does not repeat itself exactly. The breakup of Pangea was a specific event with specific consequences. Future events will differ in detail. What remains consistent is the principle that Earth's climate is deeply tied to its physical structure. Understanding this principle helps avoid simplistic narratives. Ice ages are not random, they are not inevitable. They are the outcome of long-term processes interacting in particular ways. When we ask whether it could happen again, we are really asking whether Earth will continue to evolve. And the answer to that has always been yes. The planet beneath us is still moving, continents still drift, oceans still circulate, carbon still cycles, ice still reflects sunlight. Nothing fundamental has stopped. What has changed is our ability to notice, measure, and understand these processes. We can now read the rocks. We can trace the currents. We can model the feedbacks. This knowledge does not give us control over deep time, but it gives us perspective. It reminds us that climate is not a static backdrop for life, but an active participant in Earth's story. One shaped by forces that operate far beyond any single era. Drifting continents, lingering cold, and a world still in motion describe not an ending, but a condition. A state the planet enters and then continues to inhabit, adjusting, recalibrating, and reshaping itself without ever settling completely. By the time all the pieces we have been following come together, continents have moved far from their original positions, oceans have learned complex circulation patterns, ice has established a durable presence, and climate has acquired memory. Yet nothing stops, nothing locks permanently into place. What emerges most clearly from this long arc is that Earth does not transition from one climate to another the way a switch flips. It drifts, it leans, it lingers. Cooling does not replace warmth outright. Instead, cold gains influence without eliminating variability. The planet remains dynamic, even when ice becomes a defining feature. Continental drift is central to this persistence. Once Pangea fractured, the fragments did not simply disperse and then rest. They continued migrating, sometimes toward the poles, sometimes toward the equator, sometimes colliding, sometimes opening new gaps. Each movement altered coastlines, reshaped ocean basins, and modified how heat and moisture travelled across the globe. These movements ensured that no single climate configuration could dominate forever. Even as ice expanded and ice ages became recurring features, there were always countervailing forces. Land that drifted into colder regions carried ecosystems with it, but land that drifted away reduced ice-friendly surfaces elsewhere. Ocean passages widened in some places and narrowed in others, alternately strengthening and weakening heat transport. This constant rearrangement prevented the climate system from reaching a static equilibrium. Instead, it settled into a pattern of oscillation. Cold phases waxed and waned. Ice advanced and retreated. Sea levels rose and fell. The planet learned how to be cold without becoming frozen beyond recovery. Lingering cold is the key phrase here. Ice did not need to dominate every latitude to matter. Its presence at the poles, on high plateaus, and across continental interiors was enough to shape global climate. Ice altered albedo. It redirected winds. It influenced ocean circulation. It modified ecosystems. Even when ice retreated during warmer intervals, its legacy remained embedded in soils, sediments, and circulation patterns. This is what climate memory looks like on geological timescales. Past conditions influence future responses. Once Earth entered a cooler regime, it became easier to return to cold after warm interruptions. Orbital cycles that once produced mild fluctuations now triggered major glacial advances. The same external forcing produced different outcomes because the baseline state had shifted. Importantly, this lingering cold did not make the planet hostile to life. It reshaped life, but it did not erase it. Ecosystems adapted to variability. Species evolved to tolerate cold, migrate seasonally, or exploit new niches created by glaciation. Biodiversity changed in composition, but life continued to flourish in many forms. This adaptability is part of why Earth's climate story is not one of simple decline or catastrophe. Cooling created challenges, but it also created opportunities. New habitats emerged, nutrient cycles shifted, evolution accelerated in some lineages. Ice was not merely destructive, it was transformative. At the same time, the presence of ice imposed constraints. Sea levels fluctuated dramatically, reshaping coastlines and shallow marine environments. Continental interiors became harsher. Migration routes shifted repeatedly. These pressures influenced the direction of evolution, favouring flexibility over specialisation. The world that resulted from drifting continents and lingering cold was one defined by gradients, strong contrasts between equator and poles, sharp seasonal differences in some regions and muted ones in others, dynamic boundaries between ice and open land or water. These gradients drove circulation, weather, and biological productivity. Ocean currents, now fully established in complex networks, continued redistributing heat unevenly. Some currents delivered warmth poleward, limiting ice expansion. Others carried cold toward lower latitudes, reinforcing cooling elsewhere. The balance between these currents shifted as geography evolved, ensuring that climate patterns remained fluid. Atmospheric circulation mirrored this complexity. Jet streams, storm tracks, and pressure systems responded to the evolving distribution of land, ice, and ocean. Weather became more variable in some regions and more stable in others. Long-term averages mattered more than short-term extremes. Carbon cycling remained an active participant. Weathering continued drawing carbon from the atmosphere, though at varying rates depending on temperature, rainfall, and tectonic activity. Volcanism continued returning carbon, sometimes locally intense, sometimes globally significant. The balance between these processes fluctuated, contributing to long-term climate trends. None of these systems operated in isolation. Ice influenced circulation. Circulation influenced ecosystems. Ecosystems influenced carbon cycling. Carbon cycling influenced temperature. Temperature influenced ice. This web of interactions ensured that the planet's climate remained responsive rather than rigid. A world still in motion is therefore not a poetic idea, but a physical reality. Motion is the default state. Stillness would be the anomaly. Continents move, water circulates, air flows, energy enters and leaves. The planet never pauses long enough for a final outcome to assert itself. This perspective helps explain why ice ages recur rather than persist unbroken. They are expressions of a system capable of sustaining cold, but not obligated to maintain it indefinitely. Warm intervals interrupt cold phases. Cold returns when conditions favour it again. The cycle continues as long as the underlying structure allows it. The breakup of Pangea did not create a single ice age and then stop mattering. It altered the architecture of the planet in a way that made recurring ice ages possible. That architectural change persisted even as continents continued drifting. In this sense, the question of whether the ice age began when Pangea broke apart becomes less about pinpointing a start date and more about understanding a transition. A transition from a world resistant to long-term ice to one receptive to it. A transition from climatic simplicity to climatic memory. Once that transition occurred, Earth did not need constant reinforcement to remain cool. It needed only the absence of strong warming forces. When warming did occur, it was often temporary, overridden eventually by the system's tendency to return towards its cooler baseline. Looking at the planet today, the same principles remain visible. Ice persists at the poles. Ocean currents transport heat unevenly. Continents continue drifting. Carbon continues cycling. The details differ, but the structure is familiar. What has changed is scale and speed. Human activity has introduced rapid changes that operate on timescales far shorter than tectonics or orbital cycles. These changes do not negate the long-term processes discussed here, but they temporarily overwhelm them. Over millions of years, geology will reassert its influence. Over centuries, human actions dominate. Both realities coexist. One does not cancel the other. Understanding deep-time climate evolution does not minimize present-day change, it contextualizes it. The world still in motion reminds us that climate stability is always provisional. Conditions that feel permanent are usually temporary on geological timescales. Ice can appear where none existed. Ice can vanish where it once dominated. Continents can gather and scatter. Oceans can open and close. Nothing about Earth's history suggests a final climate state. There is no endpoint where movement ceases and balance is achieved forever. Instead, there is continual adjustment around shifting constraints. This understanding reframes how we think about past ice ages. They are not anomalies or accidents. They are expressions of a planet responding logically to its own structure. When geography favours cooling, ice follows. When geography favours warmth, ice retreats. Pangea's breakup was one such structural change. It did not force ice into existence instantly. It created conditions under which ice could thrive. The lingering cold that followed was not inevitable, but it was understandable. As continents continue drifting long into the future, new configurations will emerge. Some will favour warmth, others will favour cold. The planet will respond accordingly, not out of intention, but out of physics. For now, the legacy of drifting continents and lingering cold remains embedded in the world we inhabit. Mountain ranges shaped by ancient collisions influence modern weather. Ocean currents carved by long-gone land bridges still transport heat. Ice sheets that formed under past conditions still shape sea level and climate. The story does not conclude here because the system has not concluded. Earth remains active, restless, and responsive. Each moment is part of a continuum that stretches backward into deep time and forward into futures we cannot yet see. And as long as continents drift, oceans circulate, and ice reflects sunlight, the planet will continue adjusting, leaning one way and then another, never fully still, always carrying the imprint of its past into whatever comes next.